Good morning, everybody. Once again, just a reminder, if you haven't already, one of the things you'll always do is sign into the chat room with your full name, because sometimes if you just say Amy or Kathy or Rebecca or Jennifer, we may have more than one of those. So if you can, that just helps us with verifying our enrollment. A couple of things I want to talk about. The YouTube videos are going up. We're just hung onto the fact that we are trying to attach the chat logs to them. We haven't quite, the person who knows how to do it is on a worldwide cruise. So we're trying to get in touch with her or someone who knows how to attach those chat, but we will get them up quickly. The other thing is the signups for the interpretation class. Hobbs is full. I do want to encourage you, even if it's a long drive, to try, if you can, to come to this class. Interpretation is one of those classes that you will use every day. Every day you're a master naturalist, you're volunteering in some way, shape, or form, you're going to be using interpretation. And it is one of those classes that's so much better to be done in person. You can watch a video, but it's not the same. So if at all possible, go ahead and sign up for Lake Fort Smith. You won't regret it. Even yesterday, when I was buying birdseed, someone stopped me and said, I see the sticker on your car that you're a master naturalist. Is the training very hard? Is it a good thing to do? Will I enjoy it? So all those things are interpretation. So think about it hard. Okay, as for today's Zoom, we've got watersheds. It's kind of coordinating with the things that we heard last week, and also with how climate change is affecting Arkansas. So we're going to start with watersheds. And one of the things Kevin Beefus is going to show you, give you, is a link to this ability to trace your location to where it goes into the ocean. So your watershed. So with that said, I am going to mute everyone. So Kevin, you'll need to unmute yourself in just a second, and then we'll be going. We'll get going. All right. Thanks very much.
All right, thank you. Welcome everybody to a session on watersheds. I'm gonna go ahead and get the presentation going. Hopefully y'all can see this now. I will be monitoring chat, so feel free to put questions in there. It'll have the little chat screen. Laser's gonna move around randomly as I get that oriented. So I can try to field questions as we go. And otherwise, this is the plan for today. That you'll become very familiar with this idea of a watershed, and hopefully in more detail than you've had before, because watershed is a pretty common term. It also has other great literary uses, and so we will definitely be using it in the hydrologic context, not the literary context, but they're neat that they're the same word. We're going to try to understand a little bit about what makes up a watershed, and so what are the features that kind of make a watershed the way it is. And so it will connect really well with what you learned last week on especially the geology, but of course climate matters a lot for how much water is moving around on Earth. We're going to dive into kind of in the second half after the break, we're going to dive more into the watersheds specifically in Northwest Arkansas. That we can't go into all of them, but we'll at least do a broad overview of what they are. And then these last three bullets we'll see throughout. I'm going to introduce online tools and resources, but function, connections, and interactions of watersheds, and then the quantity and quality of water in watersheds. That will probably be something that you have extra slides if you are interested. That gets into the nitty-gritty of the hydrology a fair bit. And so we will see. I am Dr. Kevin Beefus. I'm an assistant professor at the University of Arkansas. I'm in the Department of Geosciences. My specialty is in groundwater, and so surface water and what is moving around in watersheds is a part of what I do, but primarily I work with water that's underground, and so wells and aquifers. And so that could be a whole nother talk, but that's less in your face, not quite as around. And so watersheds are a great place to start your hydrologic journey, I guess. All right, so here are just a way to start and to kind of frame our discussion and development today. Um, this is the river networks of the US. And so this is a data product that we can go into more details about, but I think it's a really beautiful representation of how connected the landscape is. That the US has these different shapes and colors, and they're connected by these veins that are our rivers and our creeks. And what's interesting about this figure, this picture, is that it has different colors for the different ways that water actually moves into um, different places. And so this big pink area here is the Mississippi River system, and the Colorado River system is this big yellow one. The Great Lakes and St. Lawrence River are up here. And so we can go through and get to know all these rivers, but they connect the landscape as well. And so that's really the focus of today, are these watersheds. And so we're going to have a little bit of interaction today. It's not just going to be me talking to you. And so I wanted to give you a poll. And so this is a poll that you can access by going either to this site up here if you're on a computer. I lost my laser, but maybe you can't see that, but pollev.com. I'll put it in the chat. Otherwise, you can scan the QR code in the top right. And so this should pull up. You can do it on your phone. You can do it on a computer, pretty much any internet connected device, and you can pick one of these, and we're going to see how everybody chooses. If you are a QR code user, I can make it just a tiny bit bigger for you. And hopefully we're going to start getting responses in here once everybody goes in. You don't have to log in. I think if it asks you to log in, you can just kind of skip that. And so you can, hopefully that'll work out. Let me know if it doesn't. So what is the name of an area on Earth's surface that collects water and focuses it to a single location? I think I'm only giving you one choice too. And so this might be a harder question than you think. All right, looks like I've got 7 so far, 8, 9, 10. How many folks we have? We have 31 on here. So I'm gonna wait until we get up to about 20, 25 responders. As if I move on to the next screen, it'll lock it up. So I want to give everybody a chance who wants to answer this. We have about 4 or 5 more of these. And so you can just keep the web page up, and it'll just update with the next question as I move on to it. So this is a way just to kind of test your knowledge and also get that going. We're almost up to 20. All right, I think that's probably enough time. If you are still working on getting in there, there will be more of these questions. I'm not taking attendance or anything like that with that. That's someone else's job. All right, so let's go ahead and see what people say. So it looks like far and away, watershed is the most popular of what everyone answered. All right, that is the topic of today. What is fun about this is that the top 4 are actually, synonymous terms for effectively a watershed. And so they have slightly different meanings in different contexts, but drainage basin and watershed are pretty much identical terms. And so just because we use the term watershed doesn't mean that drainage basin wouldn't be appropriate. A drainage area is pretty much the same as a drainage basin. A catchment has a bit more of a specialty term that it can kind of be, it's like a smaller part of a watershed, even though it can still be large, but it can have water flow into it rather than only flowing out at a single point. And so a catchment is more of a specialty term. And then a wetland, no one picked a wetland. That's good. Wetlands are kind of more of a surface area where water collects, but then it also flows out, and it's more of like a distributed diffuse system and doesn't have really that as much of a single point associated with it. That water can actually percolate into the ground or come out of the ground in wetlands. A really important part of the hydrologic cycle and water quality and of course ecosystems, but not the answer to this question. All right, so that is a way to get the definition of a watershed, that it is this area on the Earth's surface that collects water and focuses it to a single location. So that single location, we're going to call it an outlet. Usually it's a point along a river or a place where two rivers connect. That's a convenient place. The next poll is just to get a sense of who's out there. Just kind of how much experience do you have with watersheds, and how well do you know the watersheds in Northwest Arkansas? That just so I can, if I'm preaching to the choir a little bit, I can throw some things in that are maybe even interesting to people with a PhD in hydrology, that I do end up talking to people with PhDs in hydrology a good bit. There aren't too many of us in Northwest Arkansas, though, specifically in hydrology. There's only a handful, I think. All right. So it looks like we have, opportunities to learn new things about watersheds. Hopefully this presentation and the slides that you get later are an opportunity for you to continue your learning about watersheds. That, of course, an hour and a half isn't long enough to really, learn everything there is to know, even about the watersheds just around us. And so that's, this is a good opportunity to start the education. You're learning so much in your training program that, part of it is just seeing how much is out there, I think. Appreciating nature for what it is. All right, I'm going to go ahead and move forward. Thank you to those who responded. I don't want to dive too much into details that aren't needed. And so this is one of my favorite little animations, right? It's a little bit cartoony, but it shows really nicely how a watershed works. And so this idea that water is falling somewhere on the land's surface, on the Earth's surface, and then collecting at a single point is kind of represented by, we have rainfall, precipitation coming from the clouds. The little red arrows are the paths or the flow paths of water particles on the land's surface, and it eventually connects into some part of the drainage network, the river system, and then it works its way down into some other body of water, and then eventually down to the ocean. And so to get a sense of what a watershed is, we have an important boundary, and we call this a watershed divide. And you can see it's labeled a bunch of different places. And so a water molecule that drops on one side of the divide will flow into this river system, and on the other side of this divide will flow into the next door watershed or river system. And so divides are really what we look at when we're looking at watersheds, that they're the boundaries between watersheds. The other thing that I really like about this is that there's actually, you can see another set of dashed lines right here, where this represents an even smaller watershed. And so here, what we're going to have to do is we have to set up an outlet. So outlets are the places where that point where the water drains to on the land surface is how we define a watershed. And so here the point is kind of this little node or connection between the two rivers. It also, you can see, has maybe, the black line should have actually probably been drawn right here and then connected over here. And so this is a smaller watershed inside of a larger watershed. And so this is going to introduce an idea of nested watersheds that we're going to dive into a pretty good bit. The other parts that I really like about this animation, even though it is so simple, is that it has a lot of parts of the hydrologic cycle. And so an important part of the hydrologic cycle, at least for my research, is what happens if one of these water molecules or a bunch of these water molecules make it underground. And so what is the path that water takes when it goes underground, and how does it connect to the rivers or to the ocean? And change the amount of water and the cleanliness of the water that is reaching our rivers and lakes and oceans. And so this is really my research focus here. So I really like that it's represented in this animation. And the other thing that's really good about this animation is that it shows some of the influences of people, that it doesn't just have a pretty green landscape that just represents a natural condition, but of course people are huge drivers in the hydrologic cycle. And so the fact that we have agricultural areas and different amounts of urbanization in this animation really is an opportunity to talk about how are people changing the hydrology, the way that water moves, the cleanliness of the water within watersheds. And so it's not just that there is a watershed there, but what happens inside of the watershed? What are the activities inside of the watershed? How much of the watershed is a forest versus farmland versus urban? And how does that change through time? What does that mean about the health of the watershed as these things change? Okay, so this is a really nice introduction to what a watershed kind of is and looks like in a fairly fun, cartoony sort of way. I believe I have the link in the notes for this slide, and so for every image that I show, mostly I just have like big pictures. Sometimes I have some actual words on a slide. But if there is an image, I try as much as I can to have the source in the notes of the slide if you're familiar with how that works in PowerPoint. And so when you get a copy of these slides, hopefully those are available. Otherwise, you're welcome to contact me for where I got this because it is so good. All right, so just with that little introduction of watersheds, this is an open-ended one where you get to type something into this answer. So what factors and features matter for a watershed and make up a watershed? And so what are the things that go into making a watershed a watershed? And so they can be physical, they can be chemical, they can be social, they can be, this whole range of things. And so this should be a word cloud. And so it should just start populating. And as people type different things, the ones that are more popular will get bigger. But it'd be great to have, a big collection of words. I think you're able to answer more than once on this one. I'm not totally sure. And it's going to move, so it'll be a little exciting to see where all these things show up. Right, so grade, the slope of the land. A steeper watershed or a shallower watershed, so that connects to the topography. Of course, the geology is underlying it all, and the geology is in big part topography, right? You learned about that last week, I think, about how, especially in Northwest Arkansas and Arkansas in general, how much the geology and really the dip or the slopes of the geologic units influences the type of topography that we have in the Ouachitas versus the Boston Mountains, how different the topography is because of the geology. We have to have rain, we have to have water that actually enters the system. So the wetter the system, the drier the system, you're going to have different types of rivers. If you think of watersheds in Arizona versus Arkansas, those are going to be fairly different types of watersheds. I think urbanization is a really good thing to think about, especially in a growing area like Northwest Arkansas. What types of housing do we have? What types of surfaces are we putting concrete in a lot of places? Are we saving some green spaces for infiltration? Are we keeping track of where that water is going? If we do put a bunch of concrete in and a bunch of houses in, do we make sure that that water doesn't just flood the people downstream? So who's upstream of you? Who's downstream of you? How are the things changing? Really, upstream is what you probably care about most, but as a collective in humanity, hopefully you care a little bit about the people downstream too, that we are primarily in an upstream part of the US, that we don't have that many watersheds upstream of us here because we are fairly high topography for just kind of where we are in the US. All right, so I think these are a lot of cool things. I can go on to a bunch of different tangent with these different words. That these are things I didn't prepare, but what you put in here, I hope gets you thinking about all these different opportunities for kind of complexity and how watersheds work and change and exist, and that they lead to difficult problems because it involves people, it involves economics, it involves policy, it involves legal aspects, and so there's a lot of challenging things. Answering questions in the chat is great. I think that's useful. And if you can't access this little poll everywhere thing I have in the chat is great, so that I have an opportunity to interact with you as well. So thanks for that question. All right, so now we're going to move on to breakout rooms. And what this breakout room activity is going to be is I am going to assign you, I guess you're going to be assigned into a smaller group of people, and your task is to draw the watershed from this topography map. And what I've done with this topography map is I've stripped all the other information about people and roads and lakes. All the hydrology information is gone. And all I left you with were the topo lines. But they don't have labels, and so that makes it a little bit harder. And so if you would, I think in your knit folder, there is a version of this, a PDF, I think. Otherwise, you can take a screenshot of the of this. If you know how to do that, the print screen button on your computer, and then you'll have a copy of this on your computer. And so what you'll do as a group is try to decide where to draw the watershed in this topography. And so we're going to leave it for 10 minutes. And so the steps to do that is you want to decide where the watershed starts, where it ends, and if you can, draw the whole watershed. And so so go ahead and hopefully someone maybe in your team can share their screen in the workout group, and then you're all kind of looking at the same thing. That's a useful thing. And then the goal would be to talk about, why you chose what you chose, and what are the, what are you confused about? What are you confident about? And then we'll bring everybody back together and talk about this. All right, so we'll do this for about 10 minutes and then come back.
We don't really need her to do anything. We just need her to talk. So I
Right.
told her that if she wanted to set up volunteer days, that I would, or, we would get somebody to come and actually do the physical part of it, show them what to do, and she could just talk them through it. Because I really think we need to get people out to the greenhouse if we can. And but I think we have one volunteer day at Lake Fort Smith, right? Angie Richardson should
Yeah, I
have
believe so.
applied for that.
Yeah, I think if I remember correctly, it was BGO was talking about it potentially. North Song. There was what was it? Springdale. And
Trailhead.
then IRWP was going to have one. Sean was going to try to do one at the Fayetteville Library doing invasive removal on their garden.
Mhm.
Just a handful of projects. So
Did Angie
all really
Richardson?
good. I want to run one myself because I've adopted the trail behind my house.
Yeah.
And there's significant invasive populations that need to be managed, and that could be very, very easily an entire. Well, I could run one every session for
Yes.
both days and still not be done.
The bike trail.
Yeah, it's the section of Skull Creek in the bike trail that's between Sycamore and North Street. So
Is
it's
that
close to
city
campus.
property?
Yeah.
Because sometimes the bike trail is very narrow as far as the land at the city or it's public property.
Yeah.
Because we went to remove junk there at Walker Park,
Mhm.
and there's so much homeless crap on the
Yeah.
creek. And they were saying, no, you can't remove it. So,
Well, they can kiss my ass because I already talked to their volunteer coordinator and got it all approved. I don't really give a
okay,
crap what
yeah,
they have to
no,
say.
that's fine. But
I am
it's
officially the adopter of the trail by record.
okay. Okay.
I didn't mean that metaphorically or
No,
romantically.
no. I know
I
what you
actually
meant,
did.
but I'm just telling you what our experience was at Walker Park, because they were saying that as you get further and further away from the park itself on the trail, the
Yeah.
actual right of way is quite small.
Yeah, no, that's fair. It's 15 feet from the center line of the trail, technically
Right.
speaking, but because the riverway is incorporated into the city property, there's a little
Yeah.
bit more flexibility
Yeah.
there.
Yeah.
And
Yeah.
we're not at a park or anything like that. And there's luckily or unluckily for them, there's no homeless encampments or anything nearby where I'm at.
Yeah, I know. It gets to be a real problem.
Yeah. Well, I
Um,
mean, that's the entire purpose of the Greenway. We want to talk about it being a connectivity project and all that, but it was a way for them to deal with the homeless problem. That really was what it was.
So,
It's unfortunate that that's the way it is, but yeah, like especially going from Walker Park towards Mount Kessler, especially, it gets pretty rough.
yep. Well, and they, the homeless tend to camp closer to their resources.
Oh yeah.
And that's, you can understand that. They're gonna be closer to the resources of of that they have during the day. And
Oh,
so
yeah.
that's why those sections of the Greenway are more problematic.
Oh yeah. Well, I mean, especially after they disbanded with the larger homeless encampment that was kind of
Yeah.
off the beaten path, they made it the case to where these people had to seek out refuge otherwise. And you're right. places that were accessible for research purposes were the first places they chose. I mean, I get it. That's the way we disperse when we don't have cities and
Right,
towns and stuff. We do the same
right.
thing.
If you don't have cars, if you don't have ready transportation, if you don't have those things, meals and things like that, that you're going to go close by.
Oh yeah.
It's just it's a hard problem to deal with.
Yeah.
And especially when they, inhabit habitat.
Well, and 9 times out of 10, cities they talk a big talk about caring, but when it comes to actually providing resources or shelter, food,
Yep.
financial resources and mental health services for these people, they don't tend to show up.
Okay, Kevin, are you closing the rooms?
Yeah, I'll close the rooms here in a second. I'll get my screen shared again.
Yeah. I'm curious. I was telling Jane, I don't know if she heard. I'm curious to see how this went. The room that I ended up getting stuck in was absolutely silent.
Yeah,
Nobody chimed in, so I'm
yeah,
curious.
we need more cheerleaders.
Yeah,
Yeah, that's all right. We'll see. We can do it on the fly too.
very true.
All right, here we go. Let's go ahead and close them all. All right, welcome back. Hopefully some watersheds were drawn or at least discussed. And so what we're going to do now with that poll everywhere thing is try to mark where your watershed started. And so this is one where you actually can click on this. On a phone, it's going to be a little bit tough, but you'll be able to click on where you said the watershed started. And that is open to interpretation. And so that is that way on purpose. You'll see that on this one, I've actually added the lakes again. And so this one has little blue areas that are representing lakes. So hopefully you are able to see this. All right, yeah, we got little green things popping in. You're welcome to throw in the chat why you picked where you picked. That's one of the challenges of just clicking on an image. It looks like for the most part, places where the topo lines get closer together and maybe where they go from being closer together to spacing out. Oh, there's even a river in the bottom right-hand corner of this topo map. Isn't that exciting? All right, lots of good things here. We're gonna have another one here coming up next, where did your watershed end? And so you can already answered, you can start thinking about where you'll put that. All right. All right, so I'm going to go on to the next one first, and then we'll start discussing this of where it is. But it seems like for the most part, we have kind of along the left-hand side, left middle side of this, one down in the right. Oh, another one just popped up there. And so we'll have an opportunity to talk about how these fit into the idea of the watershed or watersheds within this topo map. All right, so let's go ahead and move on to the next one. So now this is the same thing, just where did your watershed end? And so implicit in this is an interpretation. And that was part of why I asked the question this way is, are you thinking like a water molecule? And so are you looking downhill or are you looking uphill? And so it's important to probably define that. If this were in a class where I was giving a grade, I'd probably be a little bit clearer with what I meant, because the way I ask these questions aren't really fair. That there is an open-endedness to this that has a subjectivity of how you interpret the question. And so it looks like for the most part, the way that everyone here was thinking about it was a watershed ending is where the water flows out of the watershed. And so that would be the outlet. And so instead of asking where your outlet was, I asked this watershed ending. So asking where the outlet would have been clearer. But it looks like most of you are thinking with gravity on this one. And so the watershed would start maybe more at a divide and end at an outlet. And so that's thinking like a water molecule. The other way to think about it is that your watershed is kind of starting where if you're standing and looking up at the watershed. And so you kind of are looking uphill. And so then your start could actually be the outlet. And then the end could be the watershed divide. And so where along the topography do you actually set up that divide? All right, it looks like a few more people were able to access Poll Everywhere here as I was talking, so that's great. Thanks for participating in this. It helps me see where people are working. And so what we're going to do now is move through a couple of additions of how kind of we build up the complexity here. And so we're going to add a couple layers little by little. And we start here. So this is what you were given. Does anyone have a sense of where this is based on our, just kind of based on the topography? Does anyone recognize where this might be? You're welcome to throw it in the chat. How about as we add layers of information, we can see who, as it starts to click, you're welcome to throw it in there. You can do it just to me, or you can do it to the group chat. If you don't want to broadcast your answer, you can just send it to me by dropping that to thing in the group chat and just having my name there. All right, so the way that we build a watershed is we have to pick an outlet. We start with the outlet. You have to pick where you want the water to flow out of. And so that's the best place to start drawing a watershed. And then you want to go uphill from that perpendicular to the topography. And so the topography isn't labeled here, and so that's not very fair. That as you have these lines of equal topography, you could either be going down or you could be going up. And so one of the questions in one of the breakout rooms that I had was, are these lakes? And so you're going deeper and deeper, or are these hills or mountains? Are you going higher and higher? And so that's an interpretation that I wanted to leave open to you. In this case, it is going higher and higher. And so the highest point on this map is probably about right here. And then the lowest point is probably right around here or down here. I think it is right here is the lowest point on this map. Okay, and so if we were to draw our outlet right here, we would want to have the watershed going perpendicular to the topography. So it would come up like this, and then it kind of gets a little bit tricky here because there are these different hills. And so we probably come around, and then this one might actually just be kind of small. It comes here, and then it would go all the way up around here. And so anywhere where you draw the outlet, you have to draw a new watershed for it. Okay, you go perpendicular to the topography to do that, and you want to have, the highest part of the watershed and kind of the largest watershed here would go right along this ridge. And so you'd be cutting across these lines of topography and going along this big ridge. All right, doesn't look like anyone's guessed the right place yet. So I'm going to go ahead and move on to the next level of information, which are the roads, which these might start getting a clue of where this is. That it is in Northwest Arkansas somewhere. All right, I have a Mount Kessler. So Mount Kessler is correct, that this is the Mount Kessler and the Kessler Mountain Park, the city park in Fayetteville. And so I-49 is this road that kind of comes north-south through here. And this is MLK that goes across. Okay, so this is the Centennial Mountain, the mountain biking park, and then Kessler Mountain is here. All right, so hopefully this starts kind of connecting. Now the question is, how much do we know about the hydrology of this area? If we add all the creeks, what do they look like? And so here are the creek layers. I took off the highways to try to make this clearer. And so you can see this is Town Branch coming through here, kind of goes right along the highway. It kind of becomes the highway here, probably going through a lot of culverts over there. You have just the side of the West Fork of the White River is down here, and so that then connects up here. You can see, all these little ponds and lakes. Some of them are connected by streams. Some of them aren't that connected. They might have a little bit of an ephemeral connection, so one that isn't perennial all year long. I just got a question of where I got these from. So I got these from the USGS. They have a PDF maker, and you just kind of draw a box of where you want your topo map to be made, and then it saves it as a PDF, and then I have a PDF editor, and so I actually collected all the different layers and stripped away information, and so that's how I did that. So I just wanted to show you a topo, or like where this is with nicer labels in Fayetteville, and so here you can see Kessler, and it should be right about where things are. So yeah, so the towers are right here on Kessler, highway goes through here, and then here's the topo lines overlying with the aerial photo. And so you can see how the topography connects with all this human infrastructure that, of course, changes the hydrology a little bit. And that actually makes trying to draw the watershed harder because we have all these concrete surfaces that change the topography, and we've bulldozed to make the roads. And so, especially in flatter areas, the topography can really be changed by people, and that then changes, where water can flow. And so, we could draw put a little water droplet somewhere here on the topography and follow it down the steepest line of descent until it hits a creek, and then out a certain path. All right. So I just wanted to give you a sense of, we kind of take watersheds for granted, maybe that, this idea of a watershed can be fairly complex, especially if you have to draw it yourself from the topography. You can think about this also if you had to go out to Kessler Park, to Mount Kessler, and actually map the watershed. If you had to stand out there, in the park and say, well, this is the divide of the watershed. Could you map the divide of the watershed? That would be even another level more challenging than using a topo map like this. And so being able to stand somewhere, in Northwest Arkansas and say, I'm in this watershed is something that's pretty special. And usually those watersheds are fairly large because they have been mapped. But if you're in a specific place, it is useful to know what watershed you're in, because then you have a sense of what's upstream from you, what's downstream from you. Are there these industrial activities, or is there a landfill in your watershed? Are there potential polluters in your watershed upstream or downstream of you? For the most part, we probably don't drink the water from the creeks, but there are animals and critters that do. And so, if we want to keep those ecosystems clean, we want to kind of understand what is contributing to the health of these, especially riparian ecosystems, the creekside sort of ecosystems. But the river network and the watersheds really connect the whole landscape. And so that's kind of one of the ideas there. All right, so just a couple more slides before we take a brief break. And so this is a map now of the watersheds of North America, not including Central America. I put the definition of a watershed here just in case that slide with the pole isn't super clear. And so a slightly different term wording. This is one, that it really highlights that a watershed is defined by this point of groundwater, of water flowing out of a watershed. And so the outlet defines the watershed. And so you can put a point anywhere on the land surface and define a watershed for it. And so what's interesting here with this this picture of the different watersheds in the US and Canada is that you can see that there are these white lines, and then these white lines are inside of areas that have a certain color associated with them. And so these are two different levels of watersheds. And so the white lines are the smaller watersheds, and those smaller watersheds then feed into the bigger watersheds that have the colors. And so this is the Upper Mississippi River watershed in the orange. I guess it goes down into the Mississippi down here too. And so you can see that all these little watersheds then feed into the next watershed downstream. So these might be actually better considered catchments because they connect water flowing one way or another. But then the colors are more the watersheds. And then you can have big watersheds like the one down here in New Orleans. And that, of course, is fed by other large watersheds. So here's the Arkansas River watershed. And you can see that that's a pretty big watershed, but then it feeds into the Mississippi River watershed. And so together they are part of the Mississippi River watershed. And so there's all these different stages of watersheds going from smaller to bigger. And so I call that nesting, that there's, it's like those Russian dolls that you have that can kind of one small one fits into a bigger one, fits into the bigger one. And so that is how watersheds work. And the other really interesting thing about this, to look at a really big, global kind of scale of watersheds, is you can see how many different watersheds at different scales, different sizes, actually cross international borders. And so they cross international borders very frequently. And so that leads to international issues, that it's not just, something that happens in the US. Of course, even in the US, we have watersheds that cross state borders. And we can keep going down to watersheds that cross city borders, county borders. And so that leads to a lot of potential for differences in opinion and how they should be managed and protected. And so that can lead to a lot of different lawsuits. The Colorado River watershed is probably the #1 litigated watershed in the US, potentially in the world, just because it does cross so many states and it isn't as wet there. And so, the water is very valuable, but that doesn't mean that all these other watersheds don't have these challenges or have the potential for issues. We're going to talk about some watersheds in Arkansas that is a very wet state that still has these sorts of challenges. All right, so one of the interesting things about watersheds in the US is that they were mapped pretty well, actually, back in the late 1800s. And so this is a map on the left here that John Wesley Powell made when he was exploring the Western US as part of his duties as basically one of the first heads of the US Geological Survey. It wasn't called that back then, but he was going out to try to understand the water resources and the watersheds of the Western US. And so these are the maps of the watersheds in a report that he made to Congress back in 1890. And what is interesting in this line is that he actually has these places of aridity. And so inside of this kind of red line where the watershed colors really are, is the place where you have to use irrigation to grow crops. And so this is the arid region of the US. And so, Western US and the mountain west is part of what it is. And so these are the places where you need irrigation. And so this is the drier areas of the US. And this is roughly the 100th meridian. And so line of longitude. And this was done in the 1890s. And if we look at that today, what has happened with climate change is actually the 100th meridian, where we need irrigation on the western side of that, has actually, with climate change, moved to basically the 98th meridian now. That it's moved over 2 degrees of longitude to where the irrigation is really needed. And so, evidence of climate change within this kind of hydrologic and irrigation type framework. The other really neat thing about this report from John Wesley Powell is that he recommended to Congress that as states were being formed in this arid region, that these colors actually be what they use as state boundaries, because he saw there being too much opportunity for conflict if the states weren't drawn, or the territories weren't drawn to fit with the boundaries of the watersheds. That since water was so important for civilization in the Western US, that the states should actually follow watershed boundaries. Of course, we know that didn't happen. If we look at the figure here on the right, the map of the US, that we have all these really linear boundaries of states. And so that has led to a lot of these legal challenges. And states, of course, when they disagree on water, it has to go to the Supreme Court. And so one of the ideas that somebody came up with, this is just a fun idea, was what if we had the United Watersheds of the US? And so instead of having these hard boundaries, but use watershed boundaries as our state boundaries. And so this is their interpretation of what that might look like, of all these different watershed boundaries as the sort of states and where they would be. And so you can see that, it makes a lot of the states a little bit harder in terms of their shapes. That probably in elementary school it'd be a lot harder to learn all the US states and what they look like. But just kind of a fanciful idea of what it could have looked like. I think we're past the time when this is possible. But I thought it was pretty neat and worth thinking about of how watersheds could have been used for these boundaries. All right, so let's go ahead and take a 10-minute break. And I'm just going to leave you with this slide on fun water art here in Fayetteville in Northwest Arkansas. And we will be back at, let's say, 10 o'clock to start the second section.
Thanks, Kevin. Okay, we're gonna take a little break and back at 10. So I'm gonna pause the recording.
We're going to get back to it a little bit. I'm sure people
Okay,
are still running back to their computers.
We're back on.
Yeah, so I just wanted to show you this neat little art exhibit. It's starting to become a bit fainter here at School and Spring Avenue, School Avenue, Spring Street in Fayetteville, kind of right off of Dixon Street. You can get onto this from Dixon, where Dixon is just down another block and a half or so from here. This is the parking garage where they give away trees in Fayetteville once a year in the fall. And so this is a really neat art exhibit that has the topography of the road, and so very carefully drawn based on the engineering documents. And so these are like the topo lines, and then the little bubbles are where water would accumulate on the road. And so you can see that there's this V shape, and that's how roads are made, that there's a slightly higher part to a road. And what that does is it forces water. If a water molecule hits on one of these lines, it'll go perpendicular to these lines. And so it actually takes a path that takes it to the curb. And so you get water draining along the side, and then it accumulates. And so there's actually a slight, this intersection is a lower than all the other roads coming into it. And so water actually accumulates here and then goes down towards what used to be the Dixon Street parking lot. That's turning into a park here now that's under construction. And so this is a really neat thing. I like to take my hydrology classes to actually walk on the road and imitate a water molecule. So you're very welcome to do that. Watch out for traffic. You'll also see that every once in a while on these storm sewer inlets that you actually have some artwork. And so there's a little bit of a representation here. They're all across Northwest Arkansas. And so this is a Northwest Arkansas wide program to remind people that these are, water's draining into these and going pretty much directly. They go directly to the creek, that they're not treated. And so it's a good reminder to, try to keep the roads clean, not to be dumping oil or anything like that on that, trying to also keep these clear, that'll make sure that the roads don't flood, that if you see these full of debris, it's a good thing to remove it. Don't sacrifice your health or safety to do that, but they serve a really good purpose. And so when those get plugged up with leaf litter and sticks and stuff like that, that can lead to some flooding hazards. All right, so for this kind of second half, it's going to be a little bit shorter side of the watersheds in Northwest Arkansas. We're actually going to get to know the watersheds of Northwest Arkansas. The good news is there's no more of those polls. So if you have that open, you can go ahead and close it. We're just going to go through kind of the watersheds of Northwest Arkansas. And so we're going to work our way down from the national and kind of continental scale down to where we actually are. And so, starting with this big picture that we've already seen before, we dive into, Arkansas is here, Mississippi River is coming through this orange area. And so here we have, this is the White River watershed, where Beaver Lake is, and we're kind of right up here in Northwest Arkansas. And so we can zoom in from this sort of large, looking at all of North America, to the state. And so now here's the state, Mississippi River's coming through here. I have the counties colored up in this, and then this is the upper White River watershed. And so, the actual full White River watershed goes all the way, down to the Mississippi, but we can break that bigger watershed up into a bunch of smaller ones and then highlight the ones that are actually up in Northwest Arkansas. And so we're going to really focus on just a couple of these that cover most of the important watersheds around here. There are, of course, lots of neighboring watersheds that are similarly important, and so you can dive into those in similar ways. Of course, these are the big population centers here, and so we're going to primarily look at the upper White River watershed, which is this one that's shaded in black, and then we're going to also look at the Illinois River watershed, which is here in going over into Oklahoma. What's interesting is that both of these are interstate watersheds. That the upper White River watershed goes into Missouri, and that the Illinois River watershed goes into Oklahoma. And so, of course, that leads for opportunities for potential conflict between states. All right, so here is another representation of these watersheds. These are kind of the major watersheds of Arkansas. And so, the colors are shown and labeled here on the right. So they're unfortunately not labeled where they are on the map. But you can see here, this is the upper White River watershed, where, Bentonville's over here too, just not labeled. I guess it wasn't big enough when this figure was made. Now it is. And then the Arkansas River watershed is so big that it actually flows out and down around, Illinois River actually flows down to the Arkansas and Oklahoma and then comes in at Fort Smith. And so that's why that's colored green. Lots of other nice watersheds here. Some of them are bayous because they're, the rivers are starting to become a little bit lower slope, lower gradient, and so they're more of a bayou. The ones that kind of just stop somewhere, usually they stop at a place where the rivers connect, and so you have a confluence, and then it goes to the bigger watershed. And so the upper and lower White Rivers, you can combine those two colors and make the whole White River watershed. I do want to give you a link down here that it has a summary of all the watersheds in Arkansas. And so you can pretty much find out a good amount of information about all the watersheds at this link. It's about 15 or 20 years old now. And so unfortunately, it hasn't been updated with new information about land cover and population. But for the most part, it has, still very relevant information. I've talked to the people who made it, and they'd love to make it again, but it's something that we need to get state funding to do to update those data. Something I wanted to do was actually overlay the geology with the watershed, so you can see a little bit about how the geology actually connects to the watersheds, because of course the geology is so important for the topography. So this is a geologic map of Arkansas. Really beautiful geology. I have this map up in my office, and so if we go back and forth between the two, you can see that there, are maybe some places where the colors line up, some places where they don't as much. But that's also interesting that maybe some watersheds actually have different types of geology. And so the way that the topography and the geology affect the watershed might change as you go down the river. All right, so just a quick view of that. And now we are going to start diving into like how these watersheds work. And what's really neat is you can see Fayetteville here is at the edge of two big watersheds. So you have a watershed that goes all the way to the Mississippi River, kind of through a lot of Arkansas. So this is the upper White River watershed, and so that's in Fayetteville. But then you also have the Illinois River watershed, and I said that one actually goes into Oklahoma, and then it takes a really different path to get to the Mississippi. So you can see a water molecule that falls on one part of Fayetteville would go all the way around and enter the Mississippi River right here, where another water molecule, if it landed in the green, would actually go into Oklahoma, take a whole different path and go into the Mississippi River really close. But the paths that those two water molecules took are totally, totally different. And so if we were to zoom in, and zoom in right here, what's really interesting is that the watershed divide goes right through the middle of Old Main on the University of Arkansas's campus. And so this is Old Main right here. This is that watershed divide. And so on the north side of the watershed is the Illinois River and the Arkansas River. And on the south side, it is the West Fork of the White River, which then is part of the upper White River watershed. And so if we actually had a water molecule fall on one of the clock towers or the other clock tower, they would take widely different paths to make it to the Mississippi River. And so there's actually an online tool to do this. And this is something that Jane was mentioning at the beginning of the session today. And this is called River Runner. And so if we should definitely put this link in the chat, river-runner.samlerner. It's someone's name, Sam, and then his last name is Lerner.com. And so you actually go and you can click anywhere in the US, really anywhere in the world. This one's for the US, and then he made another one for the world, where you click somewhere, and so you can click on your house, and you can actually watch the path of the water molecule as it makes it to the ocean. And so I did that for the two sides of Old Main. I'm going to go ahead and put this in the chat, riverrunner.com. That's right. And so what that looks like is if on the north side of the bell tower, you can see this is the path that that water molecule would take to make it out the Mississippi River Delta. And then the southern one, southern bell tower actually goes up into Missouri and then comes around. And so this is where they both kind of meet the Mississippi River. So those two parts are very similar after that. But you can see that the path of water flowing through the bell tower is very different. And so you're very welcome to do that. I think it actually has it so if you want, you can fly along Google Earth along
Yes.
the river. It's a little bit dizzying, I think. I get a little motion sick doing that, but it is pretty neat to see that as well. It's just like what that path is. So if you are on campus and you're walking around the front of Old Main or the backside of Old Main, you know, if you walk around Old Main once, you've gone through the watersheds a couple times. So you're back and forth between the White River watershed and the Illinois River watershed. So one last thing that we're going to do before we dive into the Northwest Arkansas watersheds is get to know how we name watersheds. And so there's an official naming convention, and not really names, it's a unique identifier, a number for every watershed in the United States. And this was developed by the U.S. Geological Survey. It's called the Hydrologic Unit Code System. And so what they've done is they've taken all the really big watersheds in the United States and they've given them two numbers. And so they start at 1 up in Maine. And so that is this watershed area, which mostly flows just to the Atlantic Ocean, is the 01 watershed. So the code for all of this area is 01. But what we can do is we can zoom in. And so ours is really 11, that we're inside the 11 hydrologic unit code. But they give the example here for California. I'll show how it works in Arkansas. So the biggest watersheds have two numbers. Inside of them, they have four numbers. And so 18 is this all of California. This watershed right here, the Northern Mojave Mono Lake watershed, has four numbers. And so it starts with 18. So the first two tell you it's in California. The second two tell you it's in this Mojave Mono Lake watershed. Inside of this watershed, we can actually zoom in even more and find another watershed here. And so if we look at this little watershed, so this is the zoom in of that Mojave one. And so this watershed has two more digits. So you see 1809. So 18 tells us we're in California. 09 tells us we're in the Mojave. And then this 02 tells us we're in this watershed. And what's crazy is that we keep going. And so we can keep going, zooming in until there are 16. I guess in this case, there's 12 digits. The newest version actually has 16 digits. So every two numbers is another zoom in of this nesting of the watersheds. And so every single watershed across the United States and really across the whole world has this numbering sequence, and they're actually connected to each other. And so we can pass water back and forth and do a bunch of really neat stuff on computers. And that's actually how that SAM Learner River Runner thing actually works. Is it uses these identifiers to move through the neighboring watersheds and different sizes of watersheds. And so this numbering scale is really helpful. It's maybe more of a scientific thing, but it also helps you know that if there's two Illinois rivers, which of course there are more than two Illinois rivers. I know of one in Colorado, I know of one in Illinois, and of course there's the one here in Arkansas. That the name of a river isn't enough, and so this helps us identify a specific river, especially from a policy or regulation side of things. And so the hydrologic unit code, or HUCs, we call them HUCs. And so I'm going to give you the HUCs of all of our kind of important watersheds here in Arkansas. So here's a famous watershed. It's maybe not the most connected to our daily lives, but is really important watershed for the area. Is the Buffalo River watershed. And so this is the Buffalo National River that flows through the middle of this watershed. We're Northwest Arkansas is up this way more. The hydrologic unit code for this is up here in the top right corner. So it's an 8-digit hydrologic unit code. And so 11 tells us we're in the Arkansas River system. The 01 tells us we're in the White River watershed. And then we zoom in and it's really down to the 05. And so this is kind of the unique identifier for the Buffalo River. What I've done, so what I'm showing you here is the divide, so the edge, the boundary of the watershed for the Buffalo National River. And then these little yellow dots are all the poultry houses that are in the area. And so of course there's concerns about the water quality in the Buffalo National River. There's also concerns about development. And so I've listed a few organizations that are kind of connected to the Buffalo National River here in the bottom right. I actually made this map as part of a project working with the Buffalo River Watershed Alliance. It's Buffalo River Alliance to try to understand how many feeding operations there were in the watershed. And so that's what this link is here, that it lets you kind of zoom in and understand how many current poultry houses, at least to our best understanding, there are in the watershed, and then historically in the watershed. And then it also has the hog farm that they fought back several years ago. And so it has information on that. And so opportunities to understand even land use change and how we manage a river is important. Something else fun that you can do, and since I dove into this watershed a bit for them, I actually looked at some outputs from kind of average water conditions. And so this is a representation of all the different drainage networks, different streams inside the Buffalo River watershed, and looking at what percent of total annual flow, where it comes from. And so the color scheme here is that 50% of the total flow in the Buffalo River is coming when it gets to this dark color. And so about halfway through the Buffalo River, you're getting about half of the total flow in the river, which isn't always the case. And so it was kind of interesting that that happened. But it also gives you a sense of how each one of these different parts of the network actually contribute water to the overall flow in the river. And this is on an average span. I'm getting a question. Do you happen to know where they were planning to put a new processing plant to alleviate the new conservation restrictions? So there are changes planned in the Buffalo River. I am not up to date on what they are or following it. I would guess somewhere near Ponca, but I don't know for sure. Or one of the bigger towns, I would guess, but I don't know for sure. But thanks for the question. This is the same thing, just showing kind of a smaller scale. So in this case, it's only up to 5%. Just showing you that there are all these tools for using these hydrologic unit codes and then having water actually connect to each other. That's how I calculated this with a tool called Geographic Information Systems. And really, Python programming is one of the things that I enjoy. All right, so now we have to get into the watersheds that are closer to us. This is the Illinois River watershed. And so here on the left is just the Arkansas side. I wanted to show you the kind of the full side all the way down into Oklahoma, where it kind of reaches the Arkansas River. And so this is a really nice map that shows what the different land cover types are. So the light greens are more deciduous forest. There's pastures and cultivated crops. There's urban areas kind of shown in this, I don't know, tannish sort of color. And so you can see that there's all these different types of land uses. And what's so important about this river is that it is crossing from Arkansas into Oklahoma. The hydrologic unit code again is up here. So again, it starts with an 11 because it's part of the Arkansas River system, and then it has another 11 because it's part of the, I guess in this case, it's it actually goes into the Arkansas, and then smaller digits from there. You can see that the tallies of these different colors in this area here. This watershed is of most concern because there's so much development in it that it has a big part of Fayetteville and Springdale in it. It has, the southern-ish parts of Rogers and Bentonville. And so it is growing a lot. There's also a lot of poultry operations, different feeding operations here. And the water quality in the Illinois River is not clean enough when it's making it into Oklahoma. And so Oklahoma actually sued Arkansas for basically delivering them river water that wasn't up to EPA standards. And the EPA told Arkansas that they have to get their game together. And so there is a nutrient surplus zone and management plan that's trying to be developed for the Arkansas side to make sure that we aren't delivering polluted water with mainly nutrients and nitrates, and mainly nitrates, I think some phosphates as well. And the main issue is that it goes into this reservoir, the 10 Killer Ferry Lake, which is a drinking water reservoir. And so if we're delivering dirty water to it, it's more expensive for them to clean it. And so it made it worthwhile to sue Arkansas for this. And so this is something that's actively developing, that it hasn't been completely figured out how we're going to reduce the nutrient surplus in the rivers. And so just kind of getting to know the Illinois River watershed here. The Illinois River Watershed Partnership is the main organization in Arkansas that is trying to improve water quality in the Illinois River. And so they have a lot of programs looking at reducing erosion and so sediment inputs and kind of the cloudiness of the river, as well as nutrient inputs. And so they're a nonprofit, partially funded, I think, by the state and partially funded by grants, trying to do that. There is, I think, another one in Oklahoma. Their website wasn't working for me. I think they call it Save the Illinois River. And so they're kind of the kind of more advocacy group trying to get Arkansas to keep the water clean in Arkansas as well as in Oklahoma. All right, so there's more opportunities to learn about the Illinois River watershed from those resources. The White River watershed is a big reservoir kind of system, and so the Army Corps of Engineers manages a series of reservoirs along the main stem of especially the upper White River watershed. And so you can see that this is kind of the largest scale of the White River. We're going to zoom in more to the upper White River watershed, which is more where we are in Northwest Arkansas. And so here we have Beaver Lake really, prominently shown, at least in the land cover map. 1 in 6 Arkansans get their water from Beaver Lake. And so it is a major water resource. And so that's part of our watershed. You can see, so Greenland is here. It cuts right through the middle of Fayetteville as well. I guess Greenland's here. This is Fayetteville, which is the denser city part of it. The watershed divide between the upper White River and the Illinois River kind of goes along a ridge through a lot of these towns. And so I think the rail line actually goes through a lot of this. And so where the railroad goes through Rogers and Springdale, that's kind of more or less the divide between the Illinois and the upper White. And you see that there are these smaller watersheds that are really nicely labeled in this map on the left. Anything that is above the dam in the Beaver Lake would be considered part of the Beaver Lake watershed, which is a subsection or a sub-watershed of the upper Illinois River watershed. And so we'd have to kind of slice off a little bit of this and look at the sub-watersheds here that go to the Beaver Lake watershed, because we define our outlet as the outlet to the dam. And so we'd have to then define a new watershed for it. The Beaver Watershed Alliance is the main resource for understanding more about the Beaver Lake. There is also the Beaver Lake District that really manages the water. I want to zoom in a little bit more on Beaver Lake just because it is such a big water resource for the state. It's good to know about. The water is good. This is the intakes, the new intake system of Beaver Lake. This is the old intake system down here. We have the capacity right now for 150 million gallons per day to pull it out, at least for the Beaver, for our district, the Beaver Water District. And so we pull the water actually from this little knob pretty high up in Beaver Lake, just kind of in eastern Springdale, kind of. I think it's Springdale, maybe it's more closer to Rogers. But there are other intakes for different water distribution systems throughout Beaver Lake. And so this isn't the only place we pull water out of Beaver Lake. And so that's what this is showing, that there are these different places where we're pulling water from. And so Washington Water Authority, Benton Water, like kind of more the county level water distributors are pulling water actually from a different place than the Beaver Water District. And so there are all these users of the water. We have high quality water. It's mainly limestone in this area. So it's kind of more kind of on the edge of harder water. The water's cheap. It is something that is, to be proud of, is the quality of our water and how cheaply distributed it is. And so it only costs, less than, way less than a cent, a tenth of a cent per gallon of water that you're using. At the quality basically of bottled water. It doesn't have as many treatment steps necessarily, and has to go through all these different pipes, but it is really excellent water. The peak demand right now is only a third of the total pump capacity in the winter. And so we're only using about 55 to 60 million gallons per day in the winter. In the summer, that bumps up as people are watering lawns. And so it is projected that kind of more pump capacity is going to be needed probably in the next decade or so. That 90 million gallons is not getting that close to 150 million gallons per day, but we're getting up there and we're growing so much that we are going to have to rely on more and more water from the lake. This is a zoom in of those two intakes, and so the older intake is here, the newer intake and facility is here. I think this is a treatment plant before it goes out, and so Beaver Lake is this nice greenish color. And so even where this intake is, there is some development. For the most part, it's fairly rural. But what's interesting is just zooming into it is that we do have already poultry operations that close to it. Poultry operations aren't generally thought of as being a direct water quality effect. The waste is usually dry, and so they spread it on fields. And so depending on how they spread it on fields and if they ship some of it off site, that doesn't necessarily mean that there's potential for pollution there. I would expect that they are very aware that they're this close to the water resource for 1 in 6 Arkansans, and that they are kind of under the spotlight, if you will. But it is this is the area that we live in, and it doesn't seem like there are less poultry houses, and so waste has to go somewhere, and spreading it on the ground, it eventually does connect to water. Question in the chat: does all of Fayetteville get their water from Beaver Lake, even if we're in the Illinois River watershed? So yes, yep, all of Fayetteville's water is from Beaver Lake. So the city of Fayetteville gets all of their water from Beaver Lake, and they have to pump it up over the divide. And so they pump it up to the top of Mount Sequoia. There's water towers up there. That's actually where Mount Sequoia is, where the original water system in Fayetteville was. And it's a kind of a park now that kind of has a little gazebo up top. That was the original water reservoir, the little flat area below that. They had to be able to get water to campus, and so they had to be higher than campus so that they had kept the pressure. And now they kind of put their big water tanks just kind of around the side of the park. On top of Mount Sequoia, there's another water tank. On top of Markham Hill, I think there's some water tanks. So you'll see, water towers around, and that's adding pressure that they pump the water up to the top of those, and then they can, drain it out when electricity is cheaper and keep pressure in the pipes for everybody. So yeah, no, really interesting how water is distributed. All right, so with that, these are more the slides that go into how watersheds work. And so looking at water budgets, that water in minus water out, you'll have some, if they're not equal, you'll have some amount of change in water in storage. And so you can change the water in the bucket. That's, these are just kind of these ideas that I threw in here very quickly at the end. Time is running out, so I'm not going to show you kind of all of this in a lot of detail. I did want to highlight that the U.S. Geological Survey monitors the water in our rivers at all of these different gray sites across Arkansas. And so it's expensive to do this. They're always looking for funding. They're always trying to convince people that it's worthwhile to do this. And so this is how we understand floods. This is how we understand how much water we have available. And all the water basically that the large cities use in Arkansas is from rivers. And so this network is really important. But, even though it looks like there's a lot of gray dots here, if we think about all the different rivers and how all those different watersheds are nested, that even this probably isn't that much information, that this is still fairly limited. And so with that, I am going to just go to the final slide. I threw a lot of things in here about water quality and stuff like that, but probably only have a couple minutes for questions. But happy to field anything you got.
Kevin, can you go back to the slide about water, the water pollutants that you skipped over, and maybe spend just a minute on that?
This one here?
Nope.
This is
map,
sort of the
back that one.
Yeah, so there are a lot of different water pollutants. This is actually population. This is the in percent of impaired waters by watershed, kind of relatively small watersheds. I think these are Huck 8s. That the darker the color, the more impaired according to the Environmental Protection Agency. And so, you want to be in the lighter colors. The good news is that most of Arkansas is in the lighter colors. You can see, like the western part of Tennessee is less so. And so, for the most part, water is an amazing, it's amazingly clean in Arkansas. Part of that is that we don't have that large of a population, but maybe that's changing. And so as population grows, it can create these stresses and potential for impairment. And so impairment by the EPA, it kind of is set up in these four categories. And so the number one reason why water isn't clean enough in rivers in the US is actually because of sediment. And so we erode the banks of channels, we have construction projects, and so that adds mud and turbidity to and sand as well. But we add a lot of turbidity to the sediment, and that can, it blocks light getting into rivers, it can clog filters. And so sediment is actually the number one pollutant in rivers of the US. The next one are these nutrients, and so nitrogen-based ones and phosphorus-based ones, so nitrates and phosphates mainly. And so that's what we're unfortunately exporting to Oklahoma and the Illinois River. Pathogens are more like bacteria and viruses. And so these are things that get into waterways. Some of the scarier one, I guess, like E. coli is one of the more normal ones, especially from dog waste, that they have a lot of E. coli in them. So picking up your dog's poop is a really good way to help keep waters clean. But then there are also other ones. In the US, we have generally less, and we also treat our water for pathogens. But if you get kind of traveler's diarrhea and that sort of thing, that's usually from pathogens in the water. And then there's the really scary ones, the oils, the pesticides, the per and polyfluoroalkyl substances. And there's a string of scary names of chemicals that can be in the water, and those are generally from industrial activities that are pretty pervasive across the US, but they are overall less of a reason for why individual rivers are dirty. They're more connected to a specific place.
Thank you.
Mm-hmm. So how do humans affect sediment load? A percent of it would happen naturally. Yeah, so we do have erosion of river banks. What we do is we change the flow of the rivers a little bit, and we also change kind of the riparian areas that we force the rivers to go down certain paths, and sometimes that has not enough space for rivers to go, and so they erode their banks. And so that could be a major effect. Why you see those like low kind of plastic fencing around construction sites is that by having bulldozers and stuff like that, we do make it easier for erosion to happen. And so those erosion fences, sediment fences are really important for keeping extra sediment out of rivers. So that's, we just kind of accelerate the contribution of sediment to rivers. Is there a reason why the east side of Mississippi River is darker on this map? So I think that's related to Memphis. Mainly, it might be that it's a denser population, and so that's part of it. Another question, Arkansas's water better because of higher altitude? It is helpful that we are at the tops. We're near the, we don't have watersheds that feed into us, that we're not, getting water that went through Denver or something like that. And so our water is basically, we're an upland area, and so that definitely helps that we don't have watersheds that are accumulating the effects of people as we go. It's also partly because our footprint, there aren't that many people. The lower population of Arkansas is part of it. And so it's not necessarily that our activities have been less damaging. It's just that, we haven't been dense enough yet to have that happen. Probably the last question I can do, channelization of streams is bad, right? If it's not a natural channelization, if it's because of human activities, and yeah, that's kind of a deepening of the channel, I think is what Ben means. And so added erosion, it changes how fast the water moves. Yeah, generally it's bad. Generally it's undesirable too, because it can lead to the erosion of banks, and everybody kind of likes their nice low-lying areas next to the stream for, if you don't want to lose land to the river partly. And so that's one reason why channelization is bad, especially if it's accelerated by people. But yeah, I think I don't want to take away time from the next speaker.
Thank you, Kevin. That was wonderful as always.
Thanks.
Let's take just another short break. Chris,
Ma'am,
how much break do you want me to allow them to take?
as much as they are afforded. I mean, we're about halfway through the session, and I think if they need a significant break, that's fine. I can do my best to cram in the talk, but just like Michael's talk, there's a lot to cover, and honestly, we're not going to cover it all, so it's okay if we don't.
Let's just take, since we have already had a fairly long break, let's just take another 5-minute break. So give a chance to get your coffee or run to the bathroom, and we'll start back at 10:40. Pause it just back on. So you can start in just a moment.
Okay. This stuff put away. I got so many dang tabs open right now. Looking at info on this.
Yeah.
No, and thanks again for that report that you sent me. It was actually quite nice, and I was able to utilize it pretty heavily in the presentation.
Oh, you're welcome. Somebody sent, I can't remember, one of the board members sent me that, I think. Maybe it wasn't a board member, but somebody sent me that.
Yeah.
And yeah, I thought it was very interesting, even though it's a couple of years old, but
Yeah.
considering when it was written that they were seriously looking at it.
Yeah.
Okay, so for those of you who were not listening in the last few minutes, this is a new presentation for us where we've tried to look at climate in several ways. And Chris, who's also going to talk to us about basic plants, agreed to look into how climate change is affecting us as well as overall. So Chris, if you didn't know, is our president-elect. He will shortly be our president. For reasons that it's too complicated to go into. He's going to kind of take over in mid-year. But anyway, it's yours, Chris. Take it away.
All right, let me go ahead and get myself turned back on here so y'all can see me.
Oh, one more thing. If you set your view at when he shares his screen, speakers side by side, you can see him as well as his presentation. I think that's very helpful in watching the video.
I think you were correct. So let me get myself switched back around here. So all good to go. And then we will get right after it. All right. So I'm going to go ahead and start my presentation. And then we'll talk a little bit about climate change in Arkansas. All right. Go ahead and share screen. It's going to temporarily pop up on the wrong side. Go. All right, Jane, are you seeing it in the right order?
It'd help it. I would unmute. Yes, I can see your screen. It seems
Okay.
to be moving too.
Okie dokie. Just wanted to make sure I didn't have the presenter and the slideshow view swapped. All right. So as Jane stated, this is going to be a new presentation that we've come up with to kind of capture climate change in Arkansas and how we can expect things to change or how we can expect the natural state to be impacted by kind of the novel temperature and precipitation conditions that we're experiencing under climate change. Before we get into that, though, I just wanted to run over a couple things and introduce myself to you guys. Typically, I do this in my plant lecture, but considering we're getting to meet face-to-face a little bit earlier, figured I'd go ahead and introduce myself and get that knocked out of the way now. So as Jane said, my name is Chris Burkhart. Just a little bit about my academic background, so you are all aware of where I'm coming from and where this knowledge is derived from. I did get my bachelor's of science in biology here at University of Arkansas, although I always like to say that I started at Arkansas State, and that will always be my alma mater. But of course, I did get it here, and I finished here, and I'm very proud that I did. Following that, I got a graduate certificate in geospatial technologies, basically learning the ins and outs of modern mapping softwares and other hardwares and other technologies. And I'm currently getting a master's degree in biology here at the University of Arkansas, where I am studying the effects of habitat conversion, land change, and land use change on monarch butterflies in the contiguous U.S., otherwise known as CONUS. Outside of that, I am a maker, aka I like to make things that I want for myself, and that's everything from art to costumes to woodworking and so many other hands-on and invested hobbies. I'm also an avid runner, trying to do my dangest to do 5Ks and run at length on the regular for physical and mental well-being. And of course, which should be evident via being here with you, Master Naturalist in training, as well as upcoming into the board and presidency, I'm a lover of all things nature. As far as my involvement with Arkansas, I have been here for many, many years at 33 now, having moved here when I was 2. It's actually not 29 years. It's actually now a 31-year resident. I am from North Central Arkansas, from Mountain Home. I have been a master naturalist with us in this chapter since 2021, where I then went to graduate and start teaching classes. And I've been very fortunate and privileged to be teaching the plant basics class from the year following my graduation on till now. I was even fortunate enough to join the Northwest Arkansas Master Naturalist Chapter board as an at-large member, roughly representing education. And like Jane said, I will go on to become the president here in the next month or so and officially be representing you all. So if you need anything or you have questions or any curiosities as you carry on through your knit training program and looking forward towards the organization, please do reach out. Make sure that you guys have access to my email and you can contact me with any questions, concerns, or just general curiosities about organizational practices, opportunities, and that kind of stuff. Although I'm sure Jane and everyone in education, of course, Lynn Hare, will do their best to inform you before all that. And I like to, of course, just share some pictures, kind of capturing what I do and who I am. So outside of obviously all of those things I told you, I also am just absolutely obsessed with plants. So you oftentimes, like in the upper left-hand corner photo, will see me face down, fanning up, looking at plants, mushrooms, and other small organisms that otherwise might get looked over. Also a little bit of an amateur nature photographer, or at least trying to be and get better about that. And so often when I'm out hiking, if I'm not looking at plants and fungi or little bryophytes, I am trying to capture pictures of those same organisms or just the scenery in general. And of course, I will say probably more so than anything, I love the community side of conservation and education. And that's why I had the featured picture of myself and one of my former volunteer friends, Harrison Smith, and of course, a couple of my students who I got to mentor over this last summer. We're doing an ecological research experience program. Super duper fun. And hopefully that all shows in my presentations to you guys. So without further ado, let us look at climate change in Arkansas. Prior to getting into the specifics of Arkansas, though, we really ought to take stock of what's happening at large. So we'll first look at the big picture. And so by big picture, I mean global, and we're going to start ourselves there. And from there, we will slowly work our way down to the state level, where we will focus in on the specific effects of temperature and precipitation and how they've modified habitats, and what we might expect of our organismal groups in the state with those new climate change scenarios. So climate change at a global scale is, a very interesting pattern, because what we would previously have called global warming is not necessarily the case. And in fact, we oftentimes see a much more complex and nuanced picture where on average, the mean annual temperature is up roughly 1.07 to 1.18 degrees C, or roughly 212 over the 20-year average. And that pushes us also above the 100-year average. Kind of interestingly along this schema is that the 10 warmest years of the last 2 centuries have all occurred in the last decade, which in my mind represents a pretty significant departure from the average warming schema and the average temperature. And with that change, the global annual temperature increase, or rather the rate at which temperature is increasing year over year, is up. By some estimates, it's as much as 4 times and then continues to accelerate. So not only is the picture more complex in the form of, well, not all temperatures are up, some are down, some are up, some are just at a baseline where they are, but also that the rate at which this problem and continued risk is accelerating is growing even more as time moves on. So the idea that temperature is only increasing over time is not the whole comprehensive picture, but just a small portion of the total. In these figures to the right, we can just see some interesting representations of temperature and then temperature anomalies, where the upper figure represents a kind of rank percentile of temperature averages of land and sea, where the redder or the rightmost colors are the warmest and near white being almost average, and then the cooler colors of the left-hand side colors of the legend represent the record colds or the lowest ranking percentiles of temperature. And then down here at the bottom, we can just see that this figure represents departures from the norms, aka how far deviated was it from what would be expected of the 20-year of the century average, and how much of a temperature difference you saw in each of those respective years. Precipitation, we see kind of a similar picture where the subtlety and nuance and kind of represented patterns are not as simple as just it's simply wetter, it's simply drier, but rather it is a complex, highly varied, and sometimes more extreme version of the same precipitory patterns as we had previously seen, where extreme weather events are becoming entirely more common. That does include precipitation, where we saw on average more global flooding, both coastally and in the interior of our land masses, whereby tropical storms were more likely to hit ground and last longer and produce more rain, and interior flooding of riverways, lakes, and other watersheds was more likely to occur. Conversely, though, we also see an increase in overall droughts. And when there were extreme weather events, we generally saw that they repeated more frequently, aka when there was flooding, there was more likely to be repeat flooding, and similar across all kinds of extreme weather events. On average, we saw sea rise increase. Obviously, we know that with the increase in temperature and increase in precipitation and thus inputs into the water cycles, that there is likely to be greater and greater sea rise as time goes on, both from natural warming of the long-standing planetary cycles as well as from anthropogenic glacier loss due to climate change. The global mean sea level is up from 1901 to 2018 by roughly 0.2 meters, increasing at an average level by 1.3 to 3.7 millimeters per year, which doesn't seem like a lot and certainly wouldn't necessarily be a lot in your lifetime or mine or anyone's, but over the course of many centuries and in the grand scheme of geologic time can represent a pretty significant change to sea level and thus an increase in overall sea level. Of course, looking at the picture, we see kind of a similar story as we did from the previous figures, where kind of this upper figure represents the land-only precipitation anomalies, where the browner or the lefter colors are below the average, meaning there was less rainfall in those areas or on those dots than there were in previous years. And conversely, on the right-hand side of that legend, or in the colors to the right, the more blue colors, that is an increase in precipitation or in departure from the norm. Kind of similarly, we see that bottom picture represents the leftmost colors of the legend, or the tanner colors, a percent of normal, less than, or roughly at normal, versus the right-hand side, which goes into the greater than 100%. So there at the middle, we have roughly 100% or normal, if you will. And so looking a little bit closer, we draw down into North America, where in North America, on average, what we saw was the mean annual temperature was up. And if we wanted to give it a number, we'd say that it's roughly 2.01 degrees C or 3.62 degrees Fahrenheit above the century average. 2023 represented the warmest year and the highest winter temperature deviation. So it's the warmest year on record as a national average. And what that winter temperature deviation represents is a significant deviation from the average temperature, meaning that for us in 2023, we saw some of the warmest January and February temperatures compared to the long-running average. And in the grand scheme of what that could potentially signal, it is an on-average warming of winter conditions throughout the nation and potential risk of a compressed or kind of, reduced winter season. So it's a significant change to seasonal patterns and thus change to all available environmental conditions for habitat across the nation. And the rate at which our temperature is increasing as a nation is roughly 0.34 degrees C or 0.61 degrees C. And that does follow a similar pattern to the global average, though it is slightly underneath. And you'll kind of see that as we draw down that the pattern between the global, national, regional, and state levels is varied. And there is subtle differences between, but on average, we see the same kind of patterns represented regardless of scale, though slightly different in some instances. Go back to those figures. Let's look at those a little bit closer. Here in this upper figure, we see some interesting representations of temperature in another form of a ranked percentile, where the appearance of blue colors or the colors on the left-hand side of the scale represent warmer record months or warmer record years or by state, and the right-hand side or the red colors represent record warmest states. And so here we can just kind of see this ranked percentile where a handful of the southern states have a high record average, and most of us are falling into this much above average category with a handful above average, and then one in the form of Nevada represented as near average or potentially below average, depending on how you interpret that color. And then, of course, we just see kind of an average annual mean temperature represented in this bottom figure, just to kind of highlight kind of the variation in temperature that we see across the CONUS in the form of average temperature for 2023. Moving on to precipitation, we see the same kind of highly varied, inconsistent patterns across the nation where there's no kind of rhyme or reason other than what might be represented roughly by geography. Otherwise, we see some interesting patterns. So we've got a widely varied precipitation level where on average, we're actually below the, we're on the national level, we are below average for the CONUS, roughly 0.48 below the historical average, ranking this year actually as the third driest in a 129-year period, which in the grand scheme of precipitation and what that means for overall national hydrology, water availability, and potential as a potential resource for habitats and organisms, it is significantly reduced. And we expect this pattern to continue overall historically. Within the nation, we saw some extreme regionally specific weather events, whether that was hurricanes falling on the coast in a more frequent and more severe manner, or the series of atmospheric rivers that ran across much of the West and brought down with it some intense winter weather. Or, in short, some examples that we saw as far as extreme weather events were that also brought record rainfall were 17 storms, 4 floods, 2 tropical storms, like I previously mentioned, a series of 2 tornado outbreaks, a winter storm, wildfires, and a pretty significant heat wave that caused fatalities in some instances. And as has been the pattern across previous years, we also saw that drought persisted across much of the Great Plains. And as we dive down into the regional scale, we'll also see that the Mississippi River experienced significant droughts for one of many years in a row now. Looking back at the figures, we just see a basic precipitation match where we have an average for 2023 of precipitation across the U.S., where we see most of the south, east, south, and obviously along the coast in the upper northwest and going down into Northern California experience on average somewhere between, let's say, 35 to 80 inches of rainfall, which was roughly normal, but slightly below the average. Then moving in from this coast and up into the Great Plains, the Midwest, the South, and obviously into our deserts. And then the shade of our mountains and in a more mountainous terrain outside of the Appalachians, we saw significantly less rainfall from 0.5 up to that same roughly 35. And then down here at the bottom, we can see the precipitation percentage of normal, just like we saw in the global scale map, where on average, we were down in the 50 to 70% range, maybe up to 90 for the nation, where in some areas we saw significantly more rain, like here in Wyoming, in the southwestern portion of Nevada, as well as in southern and most of Southern California. But even still, this frames kind of this new, complex, and more nuanced picture where, even areas of historically dry habitat, like, in California, especially the interior of the continental interior of California, Nevada, and some of these other places like even Wyoming, where we would see significantly less rain, we are actually seeing patterns of precipitation that exceed normal values. And then in other areas, conversely, where we'd expect there to be significantly more rainfall in, let's say, the wetter habitats in the U.S., like where we are, more north of us, and then south down towards the coast of Florida and in Florida in general, we don't actually see nearly as significant rainfalls. So there's a lot of mixed kind of bags as far as precipitation and temperature, and it's important to remember that things are varied and not always intuitive. Looking forward towards an even more complex picture, which I couldn't even begin to fully capture as I am not super familiar with marine systems, is the rise in sea level, which we see over the last over the 20th century, that we rose in sea level on our coast approximately 28 centimeters, although that is highly varied depending on what part of the coast you're actually taking your sea level measurements from. And that the sea level rise, just like with the global picture, is on average about the same level of increase or accelerating at a similar rate. Some estimates put it at 2 times, others at 4, and so on. More conservatively, let's just say that it's roughly 2 times increasing. So if you were to see that along a curve, it represents a pretty steep curve upwards. And with these figures, we can kind of just see in general what was contributing to it and how far deviated from the regional sea level we expect to be and what impacts that might have. So here in this upper level figure A, we see that we have an approximation of the contribution by year of the different melting ice sheets, as well as just thermic variation and so on. So where we got, glaciers represented in red, Greenland ice sheet melting in green or blue, Antarctic ice sheet in green, terrestrial water storage, aka natural water cycling from continental sources, in yellow, and thermospheric expansion in red. Here on this right-hand side in the contiguous United States versus global mean sea level, we can see where we match up compared to the global average, where on average, we see a steady increase in global mean sea level, represented by this blue line here, which it vacillates up and down, depending, as it always does. There's natural variation in the system, but on the whole, we see that same kind of variation for the regional sea level or the contiguous U.S. sea level, but we are also slightly above average, but also below it, and sometimes. So we maybe see a little bit more varied regional sea level rise than is true of the global picture, which could potentially be indicative of greater climate extremes or higher variation in our system, and thus potential risk for greater catastrophic effects from flooding and sea rise. Here down at the bottom, we see the annual probability of the sea level being above or below an average value, where with increase in regional sea level distributions, we see an increased risk from those events and from that sea level rise. And then off to the right-hand side, we can see where the sea level rise above the mean would be expected to be under different climate scenarios and how far deviated that it can be depending on the scenario we're looking at. And with all things true of increase in sea level rise or increase in water level is especially true of increase in sea level, that there is an associated risk of exacerbating local flooding events and disrupting local hydrology. So while it is true that sea level rise will disrupt and affect those things on the coast, just like we have seen historically in the coast of Florida, Texas, and in Louisiana, in unfortunate, historically detrimental recent events, we will also see that to be true at the national scale for other flooding events, which we'll cover a little bit more as we carry on through the regional and state level climate change impacts. So now we move on to the regional effects. So we'll look at the South, kind of the Southeast, depending on who you talk to and what agency's report you're looking at. We see a little bit of mixture of different states into what is the Southern and Southeastern region. So expect there to be just a wee bit of inconsistency with how we define the region, but we'll try to capture as much of the important climate data and patterns as we can. So just like we did for the global and national levels, we'll continue to look at these things under the lens of temperature, precipitation, and rising of sea level where it is appropriate. So for us, in the South, temperature was a big deal in that we had a record-setting year for temperatures where temps were above the century average. So temperature, of course, is, and what should be stated of all climate patterns is these are large scale, large time scale, and geographic scales often, although we do compress them down into small geographic scales. But we saw temps above the century average. So that was for all states within this region. So of the southern region that we're talking about here, there are 6 states, and that is Texas, Oklahoma, Arkansas, Louisiana, Mississippi, and Tennessee. In later maps, you'll also see the inclusion of Alabama, Georgia, and Florida in the southeastern region. So expect that to come. All right. This year was ranked first in a 129-year record, meaning that it is the hottest year on record across the South that we have experienced in 129 years. With all states in the region being roughly warmer than they were from the 1991 to 2020 average, where Louisiana, Texas, and Mississippi all had record highs. Arkansas was actually ranked warmest, 4th warmest in the nation, followed by Tennessee and 5th, and not too far down the line, Oklahoma was the 10th warmest of all states in the CONUS for this year. And yeah, all states within the southern region were in the top 10 warmest for the nation. So overarchingly, what we saw is, despite even in the U.S., we saw on average warmer and in some instances lower temperatures. In the South specifically, we saw warmest on record temperatures in all states, which represents a pretty significant departure from the normal So in this upper map here, we also see a kind of interesting picture typified by these colors where we see the average daily temperature in degrees Fahrenheit represented. And for the most part, we see the hottest temperatures at maybe 75 or somewhere in the rank of 75 to 80 degrees Fahrenheit, moving all the way down to an average temperature of 55 to 60 degrees, where for the most part, where we would expect, we're going to see southern portions of this region to be hotter on average, with Texas at its tip, along the coast being the warmest, and slowly as we move up away from the coast into more northern areas, we see on average cooler temperatures. And in fact, in Tennessee, up there towards the mountains in the eastern portion of the state, we see even greater or even lower temperatures represented in the 50 to 55 degree range. Outside of this average pattern of temperatures that we see here, if we look down at this bottom figure now, we can actually see how far deviated they are from the expected average based on the 100-year pattern. And what we find is that most of the South, let's say within the Texas, Mississippi, Louisiana, and in some parts Arkansas, experienced temperature departures on average of 3 to 5 degrees higher than would be expected if you were following the 100-year average. So that is a significant temperature departure. And while, 5 degrees may not seem like a significant change in temperature, as, we are well equipped to dealing with temperature variation and we can, air condition ourselves, our natural habitats do not have that same luxury in this. These temperature departures can means very, very significant impacts to overall life history events, aka like reproductive success, juvenile survivorship, and so on. So it can be a significant risk to local flora and fauna. And then even farther north up into Oklahoma and in Tennessee and Arkansas, we see that we roughly follow the same pattern, although we have a little bit less of a departure. But in some instances, we actually saw a decrease in average temperature kind of down there in the Ouachita Mountains region where you see that green and yellow spot. We actually saw a temperature departure that fell into the negative category or was lesser than the average temperature expected for the year. So this idea of this continually evolving and entirely more nuanced and complex nature of climate change and the specific local effects is compounded further the smaller you get. And we'll see this kind of pattern represented over time as we move farther in. Moving on to precipitation, we see kind of a similar picture that we did at the national level, where we've got a widely varied precipitation level, whether that's total precipitation departure for normal or some rank percentile. If you went with that kind of data layer to observe precipitation is still going to follow this. We're widely varied. We've got some high areas, we've got some low areas, and overall precipitation is just kind of like the wild, wild west. It's nuts and it's all over the place. Compared to the CONUS, we were below average in rainfall. So on the whole, we saw less rainfall in 2023 than we did in previous years. And the same has been true historically for recent years. We experienced the third significant drought year in all years. Go back here just a second. Drop some of my notes. Okay, cool. The only thing I was going to say there was on top of the fact that we were below average rainfall and we saw significant drought, we, like I had mentioned earlier, for many years running now, the Mississippi River has collected significantly less precipitation and has been under significantly more drought coverage than in previous years. And so the levels of the Mississippi River are decreasing. We see the level of the Mississippi River lowering over time. Once again, we have another series of regionally specific weather events, whether it was the hurricanes falling in the south, turbulent tropical storms falling on land and not necessarily becoming full-fledged hurricanes, or some of the significant spring and winter weather events that brought down a lot of precipitation. We saw kind of wild weather within the state. I was really hoping that I was going to get to go attend the talk with our local meteorologists and learn all sorts about the crazy and wacky weather that had happened in Arkansas and in the regional South, and report this back and kind of tie it all into climate change. And unfortunately, he was asked to step away because, hey, crazy weather happened, and we experienced some pretty significant snowfall outside of our at current historically expected rainfall and precipitation patterns. But we'll capture some of that. Moving into sea level rise, we see once again this kind of highly varied, very inconsistent pattern across the entirety of the coast, where sea level rise follows the roughly national average, that 28 centimeters or however many centimeters of rise or millimeters of rise we saw. It was at max 3.7 globally millimeters. Where here we can see a cool representation on this southeastern map, formerly southern, we're moved on to southeastern, showing the vulnerability to sea level rise of these individual locations. So these are largely sea level rise monitoring stations. And then they came up with a fancy linear model to take into account historical flooding, current sea level rise, and various other factors to quantify what is risk, or what the risk level was for each of these local areas. And we saw that largely along the coast of Florida, it was medium to high risk, and then moving down towards Mississippi, Louisiana, and it's not on here, but the same was true of some other maps that I saw for Texas. There was significant more risk down in kind of like the Gulf coastal region, moving more western across the U.S. of compound effects of sea level rise and other flooding events. So this is kind of the last we'll see of the sea level conversation, as it's most relevant to the South and, of course, coastal states. Kind of departure from this whole climate conversation, we start to have our talk about what it means for land to change and for land cover to be modified, and what that means under these new climate scenarios. So we see here for the US that land cover is pretty significant, but it's also highly modified. Across this southern region, roughly 908,115 hectares of land was converted from forest to some other thing from 1985 to roughly 2019. We say 2020 down there in the figure, but it's approximately that. Of all the regions in the US, and these are the EPA regions, not the other regions, which were more for a climate panel. So that's why we see the kind of difference in the two map styles. We see that the most significant loss of any region, so the most significant loss of forest cover and other natural habitat types, occurred in the South, meaning largely that most of that land was converted to some type of development or another, whether that be urban, agricultural, or some other non-natural habitat type. That's the kind of conversion we were considering there. And that urban land cover is estimated to rise by some 9% by 2060. So not only is the picture of land cover problematic, but the continued spread of the urban-suburban sprawl is expected to compound and to grow and continually rise. And what that means is that on top of the natural impacts of habitat conversion and what that means for our local flora and fauna, that also it compounds the associated risk from climate change. I wish I had had it for a later slide, but there's really cool maps that you can look up. And if I think to, I'll try to get them to Jane so she can share with you guys, just showing kind of urban development along a, let's say, like a highway corridor. A good example of one to look at would be the historical maps on Google Earth of the I-49 corridor, where you can actually watch this kind of urban suburban sprawl, kind of in a like an infection like pattern, just slowly crawling outwards from the highway into these natural areas and otherwise unprotected habitat. So this pattern is expected to continue, and depending on how society and how cultural and development goes, we will see a couple of different patterns potentially emerging therein. Whereas the hopeful of us would expect and hope that on average, people would move more towards urban development and less towards suburban and private land ownership, converting more and more habitat towards suburban and other developmental types, and focus on stacking ourselves within these kind of urban habitats. Others theorize that we're going to continue to maintain our need for and sense of independence with less cultural interaction and continue to spread outwards into rural areas. And then there are hopes that some kind of midline between those two scenarios can be reached. And we'll talk about those a little bit later when we talk about climate scenarios. So interesting facts about the land conversion is that while, 908 to 100 and 908,115 hectares of land sounds like a lot, because it is, an interesting way to frame this is actually maybe from the perspective of some other land cover types, where that amount accounts for some 2.24 million acres of land, or if you want to put it in terms of something else, that's roughly 1.7 million football fields worth of land lost to development from forest from 1985 to 2019. So a pretty significant loss of habitat, which of course is only going to be further lost to climate change and future habitat conversion. All right, moving forward, we kind of focus in on this bottom map here, which is largely grayed out, but has these kind of interesting yellow areas represented across this southern region. And what this map represents are these, or this concept of areas of unprotected biodiversity or of biodiversity importance. And what those are a data product or a map layer that kind of highlights areas of potentially conservation significance and areas where contact of endangered and unprotected organisms are likely, meaning that these areas represented in yellow are unprotected and there are species there that are known to occur there and where their habitats technically should align for that area that are considered endangered or otherwise imperiled. So they represent a pretty significant area of concentrated biodiversity where, long story short, this fancy weighted model that shows number of endangered species, likelihood to meet them, significant conservation efforts that are not being taken there, as well as, whether or not the land is considered protected or the habitat they're inhabiting is considered protected, are all accounted for and shown as a single binary on-off layer. And the reason why I bring this up, and we'll see it represented later when we look down at Arkansas, is that these are areas that represent potential conservation hotspots where we can look for and try to encourage the protection, conservation, and stewardship of these endangered species, where, as it stands now, they are not protected. And with that, we move on to Arkansas. We are about halfway done though, so I think we'll take a 5-minute break and then go ahead and return back on to the presentation.
Okay.
We can go ahead and get back into it if we want to. All right. Well, everybody, welcome back. If you were here the whole time, I'm sure you enjoyed our little conversation. And if not, let us dig back into climate change and how it's impacting our lovely natural state. Let me get my screen shared here and we will get right back after it. All right. All good, Jane? Let me get back after it. All righty. So how might you might be asking, does Arkansas slot into all of this global, national, and regional patterns? Well, this is how. So for 2023, we'll see a little bit of a different picture represented, but we'll start here with this kind of like on average for the state and across many years. So our mean annual temperature is up roughly 0.9 degrees C or 1.4 degrees Fahrenheit versus the 100-year pattern. If you remember from the earlier parts of the presentation, that is less than the national average, which was roughly 2.12 degrees Fahrenheit. So we do see that we are on average not as warm as the national average, but we are in fact warmer than we were in previous years and in the previous century. Come on. Our historical range for the state over that last century period has been, 58 to 63 degrees Fahrenheit. We kind of see that represented here in this line that dips nearly down to 60 and all the way up to 63. So bottom representing the outermost regions of the confidence curve, and the uppermost regions here representing the 63. So we also see in the year-over-year variation that we have a lot of temperature fluctuation, with a large point represented down here, and then here somewhere between 1975 and 1985 we see a record low temperature represented as well. With respect to looking at the future of climate change, there is a possibility by some estimates that we will continue to see temperature rise, and it will do so at a steady rate up to 5 degrees warmer from 2023, or the time of the historic report, which I believe was, the one I was looking at was 2018. So up from 2018's year average by 5 degrees Fahrenheit, which once again, in the grand schemes of where we slot into things as people, not that significant of a change, but as far as organismal survival and their distributions in our natural state, that can represent a significant enough of a difference to move them to other places where they seek out more suitable conditions. Looking a little bit deeper at these maps here at the bottom, we start to look at what are the proposed and most likely climate scenarios for the state and what really for the globe. So these emission scenarios are based on the IPCC guidelines and report that has attempted to capture some potential paths forward for humans and for input into environment, as well as our influence on global climate change. So kind of looking at these scenarios, we'll frame a couple different examples using these maps, and we'll talk about what each scenario represents. So scenario A, emission scenario A1B represents a temperature difference of roughly 5.1 degrees Fahrenheit on average across the state of Arkansas. So this climate change emission scenario is characterized by an increasing but stabilizing population, where in roughly 2050 it increases but stabilizes and kind of finds itself a plateau around mid-century, where we continue onwards technologically, roughly like we are, maintaining a balance of mixed energy sources, both in the renewable and non-renewable energy sources, and things kind of can carry on. It's kind of like a slightly reduced but status quo version of an emissions future. So it's very similar to what we experience here. And now, versus the high emission scenario called A2, which is represented by a 4.9 degree Fahrenheit on average temperature increase by 2050. This scenario is the high emission scenario, where the A1B was the moderate emission scenario. This one represents a population growth that it continues upwards, increasing exponentially and not really hitting a plateau. So this is kind of like unfettered population growth, where in this scenario, technology development is pretty slow, and the adoption of new energy technologies is just as slow, if not slower, and thus the reliance on fossil fuels and non-renewable energy sources persists into the future, thus creating a situation where we have on average high or higher emissions. Surprisingly, though, we see that in regards to temperature, that's map 2 in the figure below or to the right, that our average temperature is pretty low compared to the state average for the moderate emission scenario. But what's also true and kind of interesting for us here in the northwest corner of the state, as you can see in the map, if you can see that color break, is that we have a kind of novel situation where even if the rest of the state is potentially going to be on average lower, we're still going to fall within that higher on average temperature range. So not only is the high emission scenario kind of counterintuitive in that we see on average lower than the moderate emission scenario, but in the northwestern portion, we're kind of isolated from what the rest of the state will look like. Then we compare that to the emission scenario B1, where we see, which is considered low, and it was represented by a 3.6 degree temperature increase by 2050. This scenario is one where the global population increases, but then just like with the A1B scenario, it peaks at roughly 2050 or somewhere thereabouts. But in this situation, we actually see rapid technological development, continued economic prosperity, kind of like this unified, coalesced global culture where people are working together towards common goals, and kind of like the natural development of a let's say energy and resource conservative society occurs, and thus renewable energy technology is developed effectively and also adopted effectively, and thus lower on average emissions. Kind of interestingly, if we pair these emission scenarios of temperature with the precipitation across the state, we kind of show an interesting picture. So based on these same kind of scenarios, so the 1, 2, and 3 are still representative of the emission scenarios A1B, A2, and B1 respectively, we see some interesting precipitory patterns emerge, where with A1B, we see in our moderate emission scenario, we see an average precipitation difference or percent difference of the state at 0.79 degree or 79%. So on average in the moderate scenario, we're going to see roughly normal precipitation patterns. So things should not change too much. We can see in the upper northwestern and kind of the eastern region, up, let's say by Crowley's Ridge, up in the north central part of the state, we see our highest precipitation. Most of the rest of the state is kind of closer to the normal. And then we see that in the southern portion of the state, we might fall just slightly below average as far as precipitation is concerned. That is a negative on average precipitation difference. Sorry, I didn't represent that clearly. I just want to go back. That is negative precipitation. So we're on average lower. So we're near normal, but on average still lower. Versus the high emission scenario A2, where we actually see a net increase in precipitation at roughly 1.65% across the state. Most of the upper, and let's say with the exception of the southwestern corner, this kind of south and southwestern corner, we see most of the state falls kind of here into this positive range of precipitation difference. But then here in this southwestern region, we actually see a little bit less precipitation on average. And then compare that all versus the low emissions scenario, where we see significant changes to precipitation, largely only occurring again in that lower left-hand corner, where on average we are up 1.74% precipitation across the state. And so it's kind of interesting to compare these, where you see an increase in temperature here and then slightly increased precipitation here, and so on, where we have concentrated temperatures in the northwest that are elevated, but then in this climate scenario, we actually don't really see much precipitation difference, although it is in fact positive. So what we see here is this kind of interesting effect where, and this is something that you may or may not be familiar with in regards to thinking about the natural state, is we're technically this subtropical state. Which is odd to think about in a largely deciduous environment or historically kind of temperate environment. But for all intents and purposes, via our weather patterns, we are subtropical. And so with this change in local climate, moving towards a little bit like wetter in some instances and even hotter in other instances, we see this kind of departure from what we would classically consider this temperate, deciduous type environment, moving more in favor of a tropical environment. So pushing that subtropical bar farther and farther away from the temperate side, moving towards tropical. So over the coming centuries, it may be the case that we start to see the emergence of habitat and local flora and fauna that more closely resemble some of our southern counterparts, versus what we see here historically, have seen here historically, and see here today. So that's it for the climate side of Arkansas. And from here on out, we're going to shift gears a little bit, and we're going to focus in on quantifying the specific habitat patterns and the effects that that's going to have on animals. So we're getting close to time here. We got about 20 minutes left. Apologies, but I'm going to start pacing through this a little bit quicker. So we're going to see if we can't get through it all as quick as possible. Let me check chat real quick. Awesome. Nothing going on there. All right. So moving forward, let's talk about the natural state. All right. So prior to talking about the impacts of climate change on habitat, let's first talk about what's happened already. Because despite our name, we are not the natural state so much if we consider things from a historical perspective. And that's exactly what we'll do to understand how habitat has already changed and how it will going forward. So Arkansas land cover is not what it once was. You know, some number of centuries ago, the 18 to 1700s is when a lot of this occurred. We saw significant logging impact coming through, significant conversions of our, our Mississippi alluvial plain and our other kind of delta habitat and lands to agriculture. And of course, we saw significant losses to many other habitats, including loss of forest to logging and conversion to urban or suburban sprawl, and probably more significantly than anything else, loss and conversion of prairie habitat into other land uses. So looking at forest, as they are one of the most significant land cover types in the state, especially with loss of a lot of our prairies, we can see that historically we had certain land areas that were covered in different types of forests. So looking at 1985, we had some 173,898 acres that were covered in deciduous forests, 154,623 acres that were evergreen, and then kind of the intermediate between those, we had 266,105 acres covered in mixed forests. So some combination of deciduous and evergreen forests. For our developed land at that time, so this is land that had been converted into industrial, urban, suburban, or some other human populated type of land, we had roughly 8,980 acres in 1985. We had roughly 453,347 acres of agricultural lands, and then of wetlands, which were largely concentrated into the South Central Plains and the Mississippi alluvial plains regions. We had a mixture of forested, non-forested, or traditional wetlands, and then like swamps, for instance, which are forested wetlands. We had 420,728 acres that were those land cover types. There were other types of land cover at the time, so this doesn't account for streams, canals, lakes, or any standing or running waters, any emergent wetlands, transitional zones, or anything like that. So there's many other land classes here that are not covered, but these represented some of the most significant natural and non-natural land uses at the time. Kind of extracting back and looking at just forests, we had this map. So this map kind of represents of the state that wasn't covered by agriculture, other rangeland, urban, suburban, industrial development, any kind of land converted habitat. This was the approximate cover of forests in Arkansas in 1985, where we can see up in this upper region, we see mostly, with some mixed forest and some evergreen sprinkled throughout, we see mostly deciduous forest. And historically, we find that to be very accurate, and even contemporarily, we see that to be true today in the Ozark National Forest, which is most of what is in, which is most of this large green mass here, where we do see a mixture of different forest types, including evergreen and the mixed forest as well. followed down here in this region, which is roughly the Arkansas River Valley that comes kind of through this region and drains out this way. We move then down into the Ouachita Mountain region, which is more heavily forested by evergreens. Although we still do see some patches of deciduous and mixed forest. Where there's forest, there will always be mixed forest. It should be a given, but just understand that. And then moving down here into the South Central Plain, just adjacent to the Mississippi alluvial plain, we see a heavy dominance of evergreen forest, mixed forest, and of course, being that it's largely a flood plain, we see a lot of forested wetlands. But pretty scarce out here in the east, with the exception of this region here, which is roughly the Mississippi alluvial loess plain, which is affectionately referred to as Crowley's Ridge. We see some forest, largely deciduous, which is still true today for what parts of Crowley's Ridge that are still there. But otherwise, we see a pretty barren landscape. So moving forward, we start to look at land conversion and kind of what accounts for the different land types and cover types in the state. So if we look here at this map, and we're going to move mostly to figures from this point forward with Arkansas, we see kind of some interesting patterns. So this map represents land conversion from 1985 to 2023, where the converted forest are lands that were converted to forest, either from some other type. So that's either conversion from one forest type to another, or conversion away from some non-forested type into a forested type. So that's that dark green color, the light green, kind of lime green color that you can see speckled out through some of the southern and this kind of north central portion of the state are conversions to urban shrubland. So that's from any type to urban shrubland, and that could potentially be represented by conversions from forests to shrublands or to prairies, or conversions away from agriculture back to natural areas in so many different types. So it accounts for a lot of different land class changes, but it's largely representative of that conversion to herbaceous and shrubland type habitats. And then lastly, and one of the most significant drivers of land change in any state, and certainly is the case in Arkansas, we see the conversion of things to development. So that's literally any type of habitat to development. Development being industrial complexes, quarries and gravel pits, urban development, suburban development, and so on. So this is conversion away from natural areas into, conversion away from natural areas into development. So that accounts for the land conversion between 1985 and 2023. This next layer will show kind of what was going on historically and how that frames into the context of the development of and change of land in the historical context. So we will see here that we lay now a layer underneath represented by yellow. So we still have the same converted habitat types, so converted to forest, converted to shrubland and herb, and converted to development. But now we see our historical forest represented there. So what this shows to me is that we have a good deal of historical forest still persisting throughout the state. So we've got a lot of land mass in the Ozark Mountain region, or the Ozark St. Francis National Forest here, that has persisted as forest for quite some time. Same is true just north of the north central area up here in the upper portion of the state. So, same for northwest Arkansas. We can see most of what would be the Hobbs, Eureka Springs areas, pretty historical forest, and then some of it up by Bella Vista is also still there, as well as looking down into the Ouachita National Forest in the upper and lower Mississippi South Central Plain, still possessing a lot of its historical forests. And the same is true for Crowley's Ridge. We see a lot of that historical forest still represented there, with less conversion to other types, although it's still pretty significant there. And we can even see here with this map, kind of this I-40 corridor and a little bit of 55 over there represented by those pink lines, if you can see them. But what's kind of interesting here is that we're still missing a lot of land, right? So in the grand scheme of habitat and where it's at and what it's doing, we still see significant areas of land that are not covered by anything on this map. And that's largely because historically, these areas had been converted to other types and represent agricultural lands. So moving from that last figure to this one, what we see is that of the lands, pretty significant chunks of Arkansas that were not forest, not other natural areas, we have significant agriculture. And that's everything from pasture lands to cultivated crops to orchards and so on. So it represents a pretty significant portion of the state that's already in use for agriculture. And we see that here represented in this map with a little bit of an elevation underlay. Moving forward, we kind of look towards similar ecoregions. So referring back to ecoregions, which you guys just learned, we've got our Ozark Highlands, our Boston Mountain, Arkansas Valley, Ouachita, South Central Plains, Mississippi Alluvial Plain, and Mississippi Valley Loess Plains, aka Crowley's Ridge, represented there. And what we find, and the reason why I included this picture, is just kind of the variation in topography and kind of tying into the previous talk, the waterways that are interacting with one another and flowing towards the Mississippi River. But we see that within this kind of Ozark Mountain region, we have a little bit of significant biodiversity, but we have so much down here in this Ouachita Mountains in the South Central Plains region, as well as out east in some of our what would have been historically prairie type habitats. So there are areas of unprotected biodiversity where we can definitely have some kind of impact on conservation efforts at there. And it's important to remember that within the southwestern portion of our state, there's significant areas that are not looked after or protected. And similarly, looking at shifting patterns from earlier, we see kind of this modification to hardiness zones within the state. So this kind of ties into the conversation of climate change as well as the conversation of habitat conversion, whereas most of the state was comprised of this 6B, 7A, 7B, and 8A hardiness zones. Moving from 2012 in this first figure on the left-hand side to this figure on the right-hand side, we see that we have nearly lost all of the 6B hardiness zone, moving predominantly in favor of the last four and seeing the rapid increase in land area of that 8B hardiness. So, okay, so let's talk a little bit about forests. So I talked about habitat conversion and what it's already happened. Let's talk about how that ties into the climate change picture. So in the grand scheme of forests, drier forests are more likely to fare well, aka we're going to see hotter on average temperatures across the state and less precipitation. So we might see drier forests. So this is true at the national level, although conditions may be slightly different here. Upland forests, glades, barrens, and woodlands that are historically drier are probably going to be more favored, so we'll see conversion of other types to them. Drought-tolerant species will be favored, so we'll see a move away from our species like our sugar maple, and we'll see an increase in drought-tolerant species like our red oak, our red maples, and so on. While climate change will proliferate other organisms, it will and cause reductions in others. Even still, there will be a potential for proliferation of insect parasites due to climate change, and that represents a significant risk to tree health in forests also and over. So that's things like pine bark beetles are potentially going to proliferate in the new novel climate scenarios. We will see a continued decrease in moisture that may lead to increased risk of fire. So drier forest will burn more frequently, and their dry fuel will also burn more intensely and potentially more frequently as well. Wetter forests are at greater risk of conversion, whereas they are more likely to experience compositional changes under altered moisture conditions, and those drought-tolerant species, like we talked about before, are more likely to be favored. Once again, it's like we'll see a conversion away from sugar maples, which tend to do better in wetter environments, towards sweet gums, red maples, and white oaks. And reliance on seasonal flooding will be increasingly devastating as far as its impact on their composition. And that's part of the reason why we see this kind of compositional modification. And overall in forests, especially wet forests, we know that there's a potential for decrease in basal area P and canopy cover. And just kind of the novel interaction here is that Arkansas may be subject to greater risk of invasions due to modification of climate into habitats more suitable to non-native species. Prairies represent a already significantly imperiled habitat. Like I said, we lost most of our prairie. And there's very little left in the state. Historically, it was quite a large portion of the state. We commonly refer to Arkansas as a forested state, but in fact, if you look at the historic ecoregions as well as just the known habitat that was recorded in early logging records, it was largely prairie with a good amount of forest as well. it was estimated to be roughly 2 million acres of land cover at one point in the state, although that has significantly declined. Roughly 5% of that is left. And it's largely been converted to agriculture and urban development, as they tend to be flat, relatively easily accessible areas. And of course, some of that and the conversion of the natural loss of prairie has been attributed to this fire suppression and lack of intermittent burning. Prairies may see significant change under climate change because on average increase in temperature and precipitation may increase land areas. So some prairies, like wet prairies, may increase, and other conditions as other areas where conditions become drier may also see a move towards drier prairies. Where when we increase in temperature and we decrease in humidity, we'll see a conversion to these tall grass drier prairies, and kind of away from it too. Conversely, where things get drier, where they're supposed to be wet for our wet prairies, much like our own Woolsey wet prairie, we might see conversion away from prairie. And of course, with an increase in fire frequency and duration in forests and other near adjacent ecosystems, we might also see an increase in conversion to prairie habitat. And like I mentioned, wet prairies will be especially sensitive to changing hydrology. And they might potentially, all prairies as a whole, potentially are going to see a decrease in their ability to sequester carbon as they're going to become highly unstable. Yada, yada, yada. And of course, any species that are reliant on prairie habitats like songbirds, like a lot of our pollinator insects that find their host plants in prairies, are also going to suffer, much like our monarchs are in peril today. Aquatic habitats are going to be subject to some very intense change, like changing in water chemistry and hydrology. There's going to be an overall decline in water availability that will change the hydrological conditions shaping these habitats, where a decrease in precipitation and an increased rate of evapotranspiration are going to represent some high modifications to water availability in aquatic habitats, aka less precipitation means less water in the water system, and an increased rate of evaporation leads to less water in the water system. So overall decrease in water availability, where climate change will continue to modify the level of water in our local waterways. It'll also modify stream flow by changing how much water can go where and how that affects the local landscape. And obviously that's going to be subject to human change as well, just like you talked earlier about channelizing. Yes, it is negative, especially when it's not natural, and it will continue to be an issue. An increase in air temperature will convert changes to water temperature, which will reduce the net temperature in water and will reduce the dissolved oxygen available to organisms that live in our aquatic habitats. And otherwise, changes in temperature and dissolved O2 will affect things like pH and other aspects of water chemistry and lead to subsequent changes up and downstream. And with changing water chemistry and temperature, as we have seen in the recent historical past, we in stagnant waterways like lakes, ponds, and other non-moving water sources, and even in some instances in moving water, we have seen an increase and will continue to see an increase in harmful algal blooms. And of course, as is true of any kind of modification to hydrology, when we start changing flow, rates, amounts, and channelization, we see an increase in sedimentation, or the amount of sediment out there, and then turbidity, the overall flow of the river. Where are we at? All right, we got a few minutes. We're going to keep rattling through, and then you guys can just hop right off when we're done. All right, so let's talk about what's going to happen to our organisms. So mammals are going to be pretty okay. They can move around, they can travel large distances to get where they need to be. So their generalized habitat requirements and diet, I mean, they're probably going to be okay. They're the ones that survived the last ice age, and they also are the organisms left after the last meteor impact. So, or the last asteroid impact. They're reasonably adaptable as far as organisms, and they're likely to be able to seek out the habitats they need, although some will succumb to climate change. They do, have that on average greater capacity to move around, so they're more likely to adapt. Bats are an exception to that because bats are subject to increases in air temperature that would make certain roosts unavailable, or caves. Warm caves are not going to do well for bats, so they're going to have to move out. More frequent droughts will lead to differential excess earlier as well, like early emergence from hibernation. Will lead to an increase in competition for resources and for mates and stuff like that. Decreased early season prey leads to increased competition there. So basically, if they come out earlier and things aren't alive and producing themselves, they're not going to have insects to eat and that. Water foraging species are going to be negatively impacted by any local changes to hydrology and water availability, aka if you historically hunted over a pond and it's gone, you're not going to hunt there. and this kind of drives this, changing prey availability will drive competition. Looking at birds, they have a high potential for climate adaptation as they can move, they can fly. They're incredibly mobile organisms capable of fast range shifts, aka they can start to find residence in new habitats pretty quickly. They're capable of seeking out suitable habitat, and changes in configuration, habitat composition, and land use do present a risk, but they tend to move out of those areas. Although highly specialized organisms with specific host plants or host species may succumb to the changes of climate change, and temperature and drought likely to be significant, impacting their available resources. Just like insectivorous birds will experience scarcity of insect populations as they decrease under new climate scenarios, and same is true of herbivorous birds as we lose plants to changing climate scenarios. Yep, basically said all that. Nest success likely to decline too. Whether it's talked about a lot or not, modern research is showing that brood success is indicated by local temperature variation, and so changes to local temperature schema will affect nest success. And species relying on wetlands, of course, are going to be especially at risk as we see continued land conversion away from wetlands and loss of wetlands due to changing precipitation conditions. Birds more reliant on open woodlands and glades are likely to increase as they're going to become more common habitats. Reptiles and amphibians. Reptiles will be okay. They have a moderate dispersal ability. The members are relying on wet habitats are more likely to be impacted. Obviously, it's going to be things like terts. And then some reptiles, like some snakes that tend to be in and around wetlands, will potentially be at risk of losing suitable habitat. And we should expect to see range shifts as food resources change. Amphibians are highly more at risk as they are going to be subject to the conditions of their local hydrological environment. And few species of endemics in specific mountaintops and microhabitats may potentially suffer. There's a cool story about those we don't have time to cover. Increase in temp and reduction in local moisture will decrease habitat and has suitable habitat for certain species, and those that rely on it for early life stages, like frogs and other amphibians that have tadpole juveniles, will potentially suffer due to lost ponds. And another important species like our hellbender is very, very likely to succumb to climate change pressures as its environment will wildly change. Same is true for fish. The water's going to change. They can only disperse where there are waterways that are not unimpeded by dams. So anywhere where temperature's warm, we decrease dissolved oxygen and start to change water chemistry. We're going to see modification to fish populations and decreases in some instances in migration in others. Oh, yes. Warming temperatures will disrupt spawning time and potentially influence their reproductive success. Obviously, continued inputs of agricultural runoff under new climate scenarios, as well as continued sedimentary load, will hurt fishes, and they're at high risk. The species that are dependent on small pools and shallow streams are especially at high risk, just like we have an endemic darter species here in Fayetteville that's potentially at risk. Oh, let's talk about crayfish. Crayfish are roughly the same. The aquatic species are going to be subject to the same changes and potential changes to ranges and risks from climate influence change. Whereas the decrease in dissolved oxygen, increase in temperature, and changes in turbidity and sedimentation from flooding will increase risks to these populations. And the aquatic species are especially at risk of being invaded by invasives that are adapted to these new climate situations. And then terrestrial species are going to be at risk due to their small ranged microhabitats changing due to changes in temperature and humidity. AKA the crayfish, there is a local crayfish that is terrestrial that lives in certain burrows like we have in Woolsey Prairie, and those are at risk of going away. And lastly, let's skip mussels for now and look at insects. The insects are a highly diverse and specialized group that are going to be differentially impacted. We've got a lot of them. We got a lot of diversity, but many terrestrial and aquatic species have high dispersal potential, and they may run away, but not all. Like the terrestrial crayfish, they can't move as much, so they're potentially going to see losses in their populations. And of course, any kind of continued degradation and habitat loss from these changes will impact them. The terrestrial species, especially the flying members, are going to be reasonably adaptable, being able to move to a suitable habitat. Habitat specialists, like those reliant on specific host plants, are going to be imperiled, like our monarchs are imperiled, and other host plant specific or other microhabitat specific species like Diana fritillaria, our native butterfly, is going to see range contraction, where those mountaintop habitats that are best for them contract and lose the suitable conditions. And then interestingly enough, a lot of or a good number of insects actually have semi-aquatic reproductive strategies, aka juvenile stages are fully aquatic or at least semi-aquatic, and thus any changes to local hydrology are going to impact these insects and may even prove to be fatal in some instances. So these are organisms like mayflies, stoneflies, dobson flies, obviously dragonflies, and mosquitoes are in there as well. But they are particularly sensitive to changes in water and temperature, water chemistry and temperature. And oftentimes these organisms are actually used in surveys of stream quality and health. Aquatic reproducers will be subject to the same climate pressures as other aquatic organisms, as I stated. So, today, do you have any questions? And I ran over just a little bit. Anybody at all? If nobody's got any questions, I'm gonna go ahead and stop share, and that's all I
Chris, I have
got
a
for you.
question.
You have a question? Go ahead.
So when I talk to people about climate change, sometimes they'll bring up like the heat island effect
Mhm.
and how that skews the temperature averages. How do you normally respond to that argument?
So that's why I included so much about the habitat conversion, right? So habitat conversion is partially responsible for climate change, and it feedbacks into the overall local temperature variation. So as far as organisms are concerned, they don't care whether the average temperature is hotter due to an impervious surface like a blacktop, roadways, parking lots, whatever, or it's due to the increase in temperature, the increase in ambient temperature due to global climate change by anthropogenic sources. So I would say, yeah, you're right, it does. But most effective climate models do actually account for impervious surfaces and heat islands like parking lots and roadways and the like. And that ultimately organisms don't care why it's hotter, just that it is. So as far as the climate change conversation, it's much harder to convince people that increase in heat matters so much as they just want to cherry pick the source. But in regards to the conservation conversation, animals don't care. They don't care what the source is, and they don't care what your opinions and beliefs are. They only care how they're being impacted and how their resources and their ability